Every detail in this story comes from real scientific research and observation. There is a planet in this solar system that has been overlooked for most of human history. Not because it is far away, not because it is hidden, because it is always standing in the shadow of the sun, too close, too bright, too difficult to reach. Its surface temperature climbs to 430 degrees Celsius in full daylight. Then the sun sets, and within a single night, the temperature falls to negative 180 degrees. A 600-degree swing. No other planet in the solar system comes close. Inside this planet, there is an iron core so large it violates every model scientists built for how rocky worlds are supposed to form. The core accounts for 85% of the planet's total mass. On Earth, the equivalent figure is 17%. On Mercury, the iron heart of the planet is not a detail. It is almost the entire planet. This world should not have a magnetic field. It is too small. It spins too slowly. Every theory said the dynamo should have died billions of years ago. And yet the field is there. Asymmetric, tilted, one-sided, but measurable. Real? At the poles, in craters so deep the sun has never reached their floors, there is water ice. On the planet closest to the sun, frozen, preserved, untouched for billions of years, sitting in permanent shadow while the surface above bakes at temperatures that would melt lead. The spacecraft that mapped this world spent 6 years getting there. It launched from Cape Canaveral, flew past Earth once, Venus twice, Mercury itself 3 times, bleeding off excess speed through gravity assists, because a direct trip to Mercury would have required more fuel than any spacecraft could carry. When it finally locked into orbit, it had traveled 7.9 billion kilometers to reach a planet that at its closest is only 77 million kilometers from Earth. The mission lasted 4 years. Then the fuel ran out, and on April 30th, 2015, the spacecraft fell. It struck the surface of Mercury at 3.91 kilometers per second and left a crater approximately 16 meters wide. That crater is still there, on a surface that has been mostly silent since the solar system was young. Tonight, this is where the story begins. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Mercury is the innermost planet of the solar system, orbiting the Sun at a mean distance of approximately 57.9 million kilometers. For comparison, Earth orbits at a mean distance of 149.6 million kilometers. Mercury is closer to the Sun than Earth by a factor of nearly 2.5. At its closest approach to the Sun, called perihelion, Mercury comes within 46 million kilometers of the solar surface. At its farthest point, aphelion, it reaches 69.8 million kilometers. This variation of nearly 24 million kilometers between closest and farthest approach is itself a defining characteristic of Mercury's nature. Mercury's orbit is the most elliptical of any planet in the solar system, with an orbital eccentricity of 0.206. Earth's orbital eccentricity, by comparison, is 0.017, nearly circular. The shape of Mercury's path around the Sun is noticeably elongated, and that elongation has consequences at every level, for surface temperature, for orbital velocity, for the gravitational relationship between the planet and the Sun that controls everything about how Mercury moves. Near perihelion, Mercury moves at approximately 58.98 kilometers per second. Near aphelion, it slows to approximately 38.86 kilometers per second. Earth, for context, orbits the Sun at a relatively steady 29.78 kilometers per second. Mercury's diameter is 4,879 kilometers. Earth's diameter is 12,742 kilometers. Mercury is smaller than two of the solar system's moons, Ganymede, which orbits Jupiter at a diameter of 5,268 kilometers, and Titan, which orbits Saturn at 5,150 kilometers. Its mass is 3.3 times 10 to the 23rd kilograms, roughly 5.5% of Earth's mass. Surface gravity on Mercury is 3.7 meters per second squared, compared to Earth's 9.8. A person standing on Mercury's surface would weigh approximately 38% of what they weigh on Earth. These numbers, taken together, describe a small, fast, elliptically orbiting world pressed close against the Sun. They are the beginning of a much stranger story. For most of human history, astronomers had limited interest in Mercury, not because it was unknown, but because it was nearly impossible to study properly. The problem is geometric. Mercury orbits inside Earth's orbit. This means that from Earth's surface, Mercury is always seen in the direction of the Sun. It never rises high in the midnight sky the way Mars or Jupiter do. It never sits in full darkness for extended observation. Mercury appears only in the narrow window just after sunset or just before sunrise, low on the horizon, often embedded in atmospheric haze and scattered solar light. Even with a telescope, observing Mercury near the horizon means looking through a thick column of turbulent air. The glass of the telescope is not the limiting factor. The atmosphere between the observer and the planet is. Distortion and shimmer degrade the image before it even reaches the eyepiece. There is a persistent claim, likely apocryphal, that Nicolaus Copernicus never saw Mercury clearly in his lifetime, that the atmospheric conditions above the Polish lowlands where he worked were too consistently poor and the planet too elusive for him to obtain a reliable view. Whether or not that specific story holds, it captures something accurate about the challenge Mercury presents. For centuries, this meant Mercury remained effectively unmapped. Astronomers tracked its motion through the sky with high precision. They calculated its orbit. They noted its phases. Mercury, like Venus, shows phases when observed through a telescope, cycling from crescent to full depending on its position relative to Earth and the Sun. But the surface itself remained invisible. What Mercury actually looked like, what it was made of, whether it had any structures or features worth identifying, all of that was inaccessible from the ground. The first major clue that Mercury was stranger than expected came not from a telescope, but from mathematics. In 1859, the French astronomer and mathematician Urbain Le Verrier published a careful analysis of Mercury's orbital motion and identified a discrepancy that could not be explained. Mercury's orbit precesses. The point of Mercury's closest approach to the Sun, its perihelion, does not remain fixed in space. It moves forward along the orbital path very slowly, completing one full circuit in approximately 225,000 years. Some precession is expected. The gravitational influence of other planets, Venus, Earth, Jupiter, the others, pulls on Mercury as it orbits, causing the orbit to slowly rotate. Le Verrier calculated exactly how much precession those known gravitational influences should produce. Then he compared that theoretical number to the observed precession. They did not match. The observed precession was larger than the calculated precession by 43 arcseconds per century. 43 arcseconds per century is an almost invisibly small number, a fraction of a degree over 100 years. But it was real, reproducible, and it had no explanation within the physics of the time. Le Verrier proposed that perhaps there was another planet orbiting even closer to the Sun than Mercury, whose gravity was producing the additional precession. He called this hypothetical planet Vulcan. Astronomers searched for Vulcan during solar eclipses, when the brightness of the Sun is blocked and fainter objects near it become potentially visible. No one ever found it. The 43 arcsecond anomaly remained unexplained for 56 years. Then, in November 1915, Albert Einstein presented the final form of his general theory of relativity. The theory described gravity not as a force transmitted between masses, but as a curvature of spacetime caused by mass and energy. Near a large mass, such as the Sun, spacetime curves significantly. Objects moving through that curved spacetime follow paths that differ subtly but measurably from the paths predicted by Newtonian mechanics. When Einstein applied his equations to Mercury's orbit, accounting for the curvature of spacetime produced by the Sun's mass of 1.989 times 10 to the 30th kilograms, the additional precession that emerged from the calculation was 43 arcseconds per century. Not approximately. Not in the right general vicinity. Exactly 43. Mercury's anomalous orbit, a puzzle that had sat unresolved since Le Verrier's publication, turned out to be one of the first direct experimental confirmations of general relativity. The planet that nobody paid close attention to had been holding one of the most important clues in the history of physics. Mercury's rotation was also misunderstood for a very long time. For much of the 20th century, the scientific consensus held that Mercury was tidally locked to the Sun, rotating exactly once per orbit, always keeping the same hemisphere pointed toward the Sun, the same way Earth's moon always keeps the same face pointed toward Earth. This belief was reasonable, given the strong tidal forces the Sun exerts on Mercury at close range, and it persisted until 1965. That year, astronomers Gordon Pettengill and Rolf Dice used the Arecibo radio telescope in Puerto Rico, the 305-meter dish built into a natural depression in the karst landscape, to transmit radar pulses toward Mercury and measure the Doppler shift of the signals that returned. Doppler shift encodes information about motion. If Mercury were tidally locked and rotating once every 88 days, the radar return would carry a specific signature. What Pettengill and Dice measured was different. Mercury was rotating significantly faster than once per orbit. Specifically, Mercury rotates once every 58.65 Earth days. Its orbital period, the time to complete one orbit of the Sun, is 87.97 Earth days. The ratio between these two numbers is almost exactly 3:2. Mercury completes 3 full rotations on its axis for every 2 complete orbits around the Sun. This is called a spin-orbit resonance, a dynamically stable gravitational coupling between rotation rate and orbital period. The resonance is maintained by Mercury's orbital eccentricity. As Mercury approaches perihelion and the Sun's gravitational pull strengthens, the pull acts on a slight elongation in Mercury's mass distribution, providing a periodic torque that locks the rotation into the 3:2 ratio rather than the 1:1 ratio of tidal locking. The 3:2 resonance had been predicted the previous year by the Italian-American mathematician BepiColombo based on orbital mechanics calculations. When the Arecibo radar data confirmed it, it was a precise alignment of theoretical prediction and physical measurement. But the resonance has a consequence worth dwelling on. Because Mercury rotates 3 times for every 2 orbits, a single solar day on Mercury, the time from one sunrise to the next, lasts 176 Earth days, twice the length of Mercury's year. There is another consequence, stranger still. Near perihelion, Mercury moves so fast in its orbit that for a brief period, its orbital angular velocity exceeds its rotational angular velocity. During this time, as seen from Mercury's surface, the Sun appears to slow its westward motion across the sky, stop, move briefly eastward, a retrograde motion of the Sun, and then resume its normal westward path. This is not metaphor or approximation. It follows directly from the geometry of the orbit and the rotation rate, and it has been verified by calculation consistent with every measurement of Mercury's orbital parameters. The Sun rises, moves across the sky, goes backward, corrects itself, and continues. On no other planet in the solar system does this happen. The first serious attempt to see Mercury at close range came in 1973. NASA launched Mariner 10 on November 3rd of that year, the first spacecraft ever targeted at Mercury, and for more than 3 decades, the only one. Mariner 10 weighed 503 kilograms. It carried 2 television cameras, an infrared radiometer, an ultraviolet spectrometer, a magnetometer, and instruments for measuring charged particles and plasma. Power came from 2 solar panels producing approximately 500 watts at Earth's orbital distance from the Sun, a figure that increased substantially as the spacecraft traveled inward toward Mercury, where solar irradiance is between 4.5 and 10.6 times Earth's. This increase in solar intensity was both a resource and a threat. The spacecraft carried sunshades and required careful thermal management to prevent overheating as it approached Mercury's inner solar environment. The mission's trajectory was designed by BepiColombo, the same mathematician who had predicted Mercury's 3:2 spin-orbit resonance. Colombo recognized that a carefully planned gravity assist at Venus could place Mariner 10 in a solar orbit that would return the spacecraft to Mercury at intervals of approximately 176 days. This was not coincidence. 176 days is exactly one Mercury solar day, one full cycle of Mercury's sunrise to sunrise period. By timing the trajectory to this period, Mariner 10 would always arrive above the same illuminated hemisphere of Mercury. The Venus flyby occurred on February 5, 1974. The first Mercury flyby followed on March 29, 1974, at a closest approach distance of 703 kilometers. The cameras returned the first close-up images of Mercury's surface in history. The landscape was dense with craters. Densely, uniformly saturated, a surface that in broad character resembled the lunar highlands, but with differences subtle enough to carry scientific significance. Crater morphologies, ejecta patterns, and the distribution of secondary craters all pointed to a surface that had been geologically active in ways that simple lunar comparison did not fully explain. The largest feature visible in the first set of Mariner 10 images was a vast circular depression situated near the equator, a basin of scale that the team named Caloris, from the Latin word for heat, because it sits near the point on Mercury's surface that receives the most intense solar radiation at perihelion. Its full extent was not visible in the first flyby. Part of it lay in shadow, but what was visible suggested a structure of extraordinary size. Mariner 10 returned to Mercury on September 21st, 1974, and again on March 16th, 1975. Each return, because of Colombo's resonance geometry, brought the spacecraft over the same hemisphere, the same face of Mercury. Always the same side illuminated, always the same side dark. By the time the attitude control gas ran out in March 1975 and the mission ended, Mariner 10 had imaged approximately 45% of Mercury's surface. The other 55% remained completely unseen, and it would stay that way for the next 30 years. What the magnetometer found during those 3 flybys was perhaps the most consequential surprise of the entire mission. As Mariner 10 approached Mercury for the first time, the onboard magnetometer detected a structured magnetic field surrounding the planet. Not a large field, not a field comparable to Earth's in any way, but a real dipolar field, organized, directional, and consistent with what a planetary magnetic field looks like when it is generated by internal processes rather than induced by the solar wind. The field strength at Mercury's equator was approximately 300 nanoteslas. Earth's equatorial field strength is approximately 30,000 nanoteslas. Mercury's field was about 1% as strong. The surprise was not the weakness. The surprise was the existence. The standard model for how planets generate magnetic fields, the dynamo mechanism, requires a large region of electrically conducting fluid inside the planet, moving in organized convective patterns driven by internal heat. On Earth, this is the outer core, a shell of liquid iron and nickel approximately 2,300 kilometers thick, vigorously convecting because the inner core is very hot and the mantle above it is cooler. The temperature difference drives circulation. The circulation generates electric currents, and the electric currents sustain the magnetic field. Mercury was expected to have no active dynamo. Small planets cool faster than large ones. The ratio of surface area to volume is higher, heat escapes more quickly, and the interior solidifies on a shorter timescale. A planet the size of Mercury should have frozen solid billions of years ago. A solid core cannot convect. A core that cannot convect cannot sustain a dynamo. No dynamo, no magnetic field. And yet the readings were clear. The field was there. Something inside Mercury was still moving. Something inside Mercury had not yet gone quiet. What that something was, what the interior of this planet actually looked like, what processes were still operating 4.5 billion years after Mercury formed, was a question that would take 30 more years and a new spacecraft to begin answering. That spacecraft was being planned. The questions were already written. Mercury was waiting. The surface that Mariner 10 had imaged, that 45% of Mercury visible to the spacecraft's cameras, was already beginning to tell a complicated story. The crater density in the oldest regions of Mercury's surface is comparable to the lunar highlands. This means that, like the Moon, Mercury's ancient terrain preserves a record of the period in early solar system history now called the Late Heavy Bombardment, a period between approximately 4.1 and 3.8 billion years ago, when the inner solar system was subjected to an intense flux of impactors, probably driven by gravitational instabilities that caused the giant planets to migrate inward and scatter vast numbers of asteroids and comets into new trajectories. The surfaces that survived this bombardment without being completely resurfaced by later volcanic activity are the oldest readable pages in a planet's geological history. Mercury appears to have large regions of such ancient terrain. But alongside those heavily cratered plains, Mariner 10 also detected smoother regions, areas of lower crater density that suggested volcanic resurfacing had occurred at some point after the main cratering epoch. Smooth plains on Mercury. Volcanic plains, probably, though with the data available from Mariner 10's partial surface coverage, the volcanic interpretation could not be confirmed with certainty. There were also features unique to Mercury that appeared in no other planetary body in the solar system. Scarps. Long, sinuous cliffs running across the surface for hundreds of kilometers, some of them thousands of meters high, cutting across craters and plains without apparent relation to impact events. These features were named lobate scarps, and they appeared to represent a form of compressional deformation. The working hypothesis that emerged from Mariner 10 analysis was that Mercury had contracted as it cooled, that the planet had physically shrunk, and that the crust, unable to simply compress uniformly, had buckled and thrust upward along these great fault lines. The estimated total contraction suggested by the scarps visible in the Mariner 10 data implied Mercury's radius had decreased by perhaps 1 to 2 kilometers over its history. A kilometer. On a planet Swy, dry 9 kilometers in radius. The entire world tightening as it cooled, its surface wrinkling like the skin of a drying fruit. These were the findings Mariner 10 left behind when its final contact ended in March 1975. Partial surface coverage. A confirmed magnetic field with no agreed explanation. Evidence of ancient cratering, possible volcanic resurfacing, compressional scarps, and a core that seemed to be doing something it should not be doing. For 30 years, this is what scientists had to work with. 30 years of analysis, debate, modeling, and waiting. The next step required a spacecraft that could actually go into orbit, not a flyby mission crossing Mercury's neighborhood at high speed, but a vehicle that could slow down enough to be captured by Mercury's gravity, circle the planet for months or years, and systematically map everything Mariner 10 could not. The engineering problem was immense, and the solution, when it finally came, would require a trajectory no one had ever attempted for a mission to Mercury. That mission was already being designed. It had a name, Messenger, and its journey to Mercury would take longer and travel farther than almost anyone outside the mission team fully appreciated. The problem with getting to Mercury is speed. Not speed in the sense of going fast enough. Speed in the sense of going too fast. Mercury sits deep in the sun's gravitational well. Objects falling toward the sun accelerate. A spacecraft launched from Earth toward Mercury, aimed directly inward, would arrive at Mercury's orbit, moving far too quickly to be captured by Mercury's gravity. It would simply fly past. To enter orbit around Mercury, a spacecraft must slow down. It must fire its engine against its direction of motion, decelerating hard enough to bleed off the excess velocity accumulated during the fall toward the sun. The fuel required to do this directly, to launch from Earth, fly to Mercury, and decelerate into orbit in a single trip, is enormous. More fuel than any realistic spacecraft could carry. The rocket equation is unforgiving. Every kilogram of fuel you want to carry to Mercury requires additional fuel to launch that kilogram from Earth, which requires more fuel to launch that additional fuel, in a cascade that quickly makes the mission impossible with any foreseeable launch vehicle. The solution, developed by trajectory designers at the Johns Hopkins University Applied Physics Laboratory, was to not go directly, to go the long way around, to use gravity. Messenger, the Mercury surface, space environment, geochemistry, and ranging spacecraft, launched on August 3, 2004, from Cape Canaveral Air Force Station aboard a Delta II rocket. Its destination was a planet 77 million kilometers away at closest approach. Its trajectory to get there covered 7.9 billion kilometers and took 6 years and 7 months. The path used 6 gravity assists. One flyby of Earth, providing a small additional velocity kick. 2 flybys of Venus, using that planet's gravity to redirect and slow the spacecraft. 3 flybys of Mercury itself, each one trimming velocity, each one adjusting the trajectory so that by the 3rd Mercury flyby, the spacecraft was moving slowly enough that a final engine burn could complete the capture into orbit. Each gravity assist worked by the same basic mechanism. The spacecraft approached the planet from a carefully calculated direction, fell through the planet's gravitational field, and emerged on the other side, moving in a different direction and at a different speed, without any fuel expenditure, the energy coming entirely from the planet's orbital momentum. The effect is small for any single planet compared to the momentum of a world. But for a spacecraft of Messenger's mass, 1,107 kilograms at launch, of which 599 kilograms was propellant, the velocity changes from 6 carefully planned gravity assists accumulated over 6 years, were enough. During the long cruise phase, Messenger operated in a carefully managed low-power state. The instruments were tested periodically, calibrated, checked. The spacecraft had to be kept thermally stable across vast variations in solar distance, flying far enough from the sun on some legs of the trajectory that solar power generation dropped significantly, then approaching the inner solar system where the intensity of sunlight required additional thermal management. Messenger carried a large sunshade, a ceramic cloth shield on its sunward face, roughly 2.5 meters by 2 meters, designed to keep the spacecraft body in shadow during Mercury operations when solar irradiance reaches as much as 11 times Earth normal. During the Mercury flybys that preceded the orbital insertion, the science team got their first new data on Mercury in more than 3 decades. The first Mercury flyby occurred on January 14, 2008. For the first time in 33 years, a spacecraft was close enough to return detailed imagery. And for the first time in the mission's history, the cameras were looking at the hemisphere Mariner 10 had never seen. The images returned from that first Messenger flyby showed terrain that had never been photographed by any spacecraft. The unseen 55% of Mercury was beginning to reveal itself. The second Mercury flyby occurred on October 6, 2008. The third on September 29, 2009. With each pass, the trajectory was refined, more data returned, and the spacecraft settled closer to the parameters needed for orbital capture. On March 17, 2011, at 0:45 UTC, Messenger fired its main engine for 15 minutes and 4 seconds, producing a velocity change of 862 meters per second. That burn, executed with the spacecraft out of radio contact on the far side of Mercury, slowed Messenger enough for Mercury's gravity to take hold. When the spacecraft emerged from behind Mercury and re-established contact with Earth, the signal confirmed it. Messenger was in orbit. The first spacecraft ever to orbit Mercury. The initial orbit was highly elliptical, a 200-kilometer minimum altitude at the closest approach point, rising to a maximum altitude of approximately 15,193 kilometers at the farthest point. The orbital period was 12 hours. Mercury's gravity field is not perfectly uniform. It reflects the uneven distribution of mass beneath the surface, and the orbit required periodic correction burns to maintain stable parameters over the months of the primary mission. The instrument suite Messenger carried into orbit was designed to answer the questions Mariner 10 had raised. The Mercury Dual Imaging System, or MDIS, carried 2 cameras, a wide-angle camera for color imaging and regional mapping, and a narrow-angle camera for high-resolution surface detail. Together, they would construct the first complete photographic map of Mercury's surface. The Messenger Laser Altimeter, or MLA, fired laser pulses at the surface and timed their return to measure elevation. Over thousands of orbits, these measurements built a topographic map of Mercury's northern hemisphere with a precision and density of coverage previously impossible. The gamma-ray and neutron spectrometer detected radiation emitted by elements in Mercury's surface material, gamma rays and neutrons produced when cosmic rays strike the ground and cause nuclear reactions that release characteristic energy signatures. This allowed identification of specific elements, hydrogen, iron, titanium, calcium, sulfur, potassium, thorium, uranium. The X-ray spectrometer detected fluorescent X-rays from Mercury's surface, produced by solar X-ray bombardment, another technique for measuring elemental composition. The magnetometer measured Mercury's magnetic field with far greater precision and coverage than Mariner 10's single-instrument flyby data had permitted. The Mercury Atmospheric and Surface Composition Spectrometer, MASES, analyzed the ultraviolet and visible spectrum of light from Mercury's surface and its thin exosphere. The energetic particle and plasma spectrometer measured particles in Mercury's environment, the solar wind, charged particles trapped in Mercury's magnetic field, and the complex interaction zone between the planet's magnetic field and the constant pressure of the solar wind. Each instrument addressed a different aspect of the same set of questions. What is Mercury made of? What is happening inside it? What is its history? And why does it look the way it does? The first major result to emerge from MESSENGER orbital data was also one of the most consequential: the complete surface map. As MESSENGER built its photographic coverage over the first months of the mission, the full extent of Mercury's surface became visible for the first time. The broad pattern that Mariner 10 had suggested was confirmed and extended. Mercury's surface is divided between ancient, heavily cratered terrain and smoother volcanic plains. The volcanic plains are not randomly distributed. They appear concentrated in the northern hemisphere and around the large impact basins, areas where basin-forming impacts punctured the crust deeply enough to allow volcanic material from below to flow up and resurface the landscape. The northern volcanic plains in particular, imaged in full for the first time by MESSENGER, represent one of the largest coherent volcanic deposits in the inner solar system, a vast expanse of smooth, relatively young terrain that covered an area of approximately 6% of Mercury's total surface. The age of these plains, estimated from crater counting, the principle that older surfaces accumulate more impact craters per unit area, place the volcanic activity at between 3.5 and 3.7 billion years ago. Mercury was volcanically active well into its history. Not forever. Not recently. But longer than the old models had suggested. The lobate scarps that Mariner 10 had detected in partial coverage were now mappable across the full surface. MESSENGER found them everywhere, large thrust faults running for hundreds of kilometers, some reaching elevations of 3 kilometers above the surrounding plains. The total shortening they implied had increased significantly from the Mariner 10 estimate. The updated calculations suggested Mercury's radius had decreased by between 5 and 7 kilometers over its history, not the 1 or 2 kilometers suggested by the earlier partial data. The planet had contracted significantly as it cooled, its surface compressing and buckling, the great scarps rising as the interior volume decreased. This is a planet that has been shrinking, slowly over billions of years. Still shrinking, perhaps, though at a rate too slow to measure directly. Then MESSENGER turned its cameras toward Caloris Basin, and for the first time, the full extent of that structure was visible. Caloris Basin is one of the largest impact structures in the solar system. Its diameter is 1,050 kilometers. It was formed approximately 3.9 billion years ago, during the late heavy bombardment period, when an object estimated to be perhaps 100 kilometers in diameter struck Mercury at high velocity. The energy released by that impact is staggering to calculate. The kinetic energy of a 100-kilometer rocky body striking Mercury at an estimated velocity of 20 to 30 kilometers per second produces an energy output on the order of 10 to the power of 26 joules. For comparison, the total energy output of the Sun in 1 second is approximately 3.8 times 10 to the 26 joules. The Calorus impact released energy comparable to a fraction of a second of the Sun's total output, focused on a single point on Mercury's surface. The basin floor is marked by a system of concentric rings and radial fractures. At the center of the basin, the original floor was pushed downward and then rebounded upward as the shock wave reflected, a feature called a central peak complex, here running to dimensions of hundreds of kilometers rather than the kilometers-wide central peaks seen in smaller craters. Around the basin rim, material ejected by the impact was deposited in thick layers extending for hundreds of kilometers outward. But the most remarkable consequence of the Calorus impact is on the exact opposite side of Mercury. 180 degrees away from Calorus, at the antipodal point, the surface is covered in what geologists call chaotic terrain, a region of jumbled, hilly, disrupted ground unlike anything seen elsewhere on Mercury. The antipodal chaotic terrain has a specific explanation. When the Calorus impactor struck, the energy of the impact radiated outward as seismic waves in all directions through Mercury's interior. Those waves converged at the antipodal point, the point diametrically opposite the impact, where they focused and interfered constructively, releasing enough energy at the surface to shatter the existing terrain into the chaotic hills and depressions that MESSENGER imaged 4 billion years later. The ground at the antipodal point to Calorus was destroyed by an impact that happened on the other side of the planet. The shockwave traveled through the entire body of Mercury and arrived with enough remaining energy to rearrange the landscape. This is what a 550-kilometer impact basin means. This is the scale of what Mercury has survived. MESSENGER also found something unexpected in Calorus Basin itself. The floor of the basin, despite being the site of the most energetic impact event in Mercury's recorded history, is not the lowest point on the planet. It has been pushed upward. Parts of the Calorus floor stand several kilometers above the surrounding plains, outside the basin. The rebound from the impact, the volcanic material that flooded the basin afterward, and the subsequent history of compression and deformation have made the interior of Calorus a complicated, layered record of Mercury's most violent chapter. The high-resolution images from MESSENGER revealed features within Calorus that no prior mission had the resolution to detect, networks of troughs and ridges forming polygonal patterns across the basin floor, evidence of extension and contraction that recorded the cooling and settling of the massive pool of impact melt and volcanic material that once filled the basin. Outside Calorus, across the broader surface, MESSENGER's imaging revealed another category of feature that was new to Mercury science. Hollows. Small, irregular depressions with bright interiors and halos, clustered on crater floors and central peaks, absent from the oldest and most exposed terrain, but common in protected or shadowed locations. These features had no clear analog on the Moon or Mars. Their formation mechanism was uncertain. The leading hypothesis was that they represented sites where volatile materials, substances with low boiling points, including sulfur compounds, possibly chlorine-bearing materials, had sublimated from the surface when exposed to solar heating, leaving behind shallow pits as the material vaporized into Mercury's thin exosphere. If that hypothesis is correct, the hollows are evidence that Mercury's surface still contains volatile compounds. That Mercury, despite its proximity to the Sun and its extreme surface temperatures, has not been entirely stripped of all volatile material. This was unexpected. Theories of Mercury's formation had generally predicted a volatile depleted surface. A world so close to the Sun, subjected to intense solar radiation and repeated bombardment, should have lost its volatiles long ago. The hollows and the messenger compositional data that accompanied them suggested the story was more complicated. Mercury had kept some of its volatiles. Where they came from, how they survived, what their presence implied about the planet's history, these were questions the mission was only beginning to frame. And beneath all of these surface features, beneath the craters and plains and scarps and hollows, the interior of Mercury was waiting with the strangest questions of all. The iron heart, the magnetic field, the liquid core. The answers to those questions were encoded in data Messenger was already collecting, in the subtle wobbles of the spacecraft's orbit as it responded to Mercury's uneven gravity field, in the precise measurements of Mercury's rotation rate, in the magnetic field readings accumulating with every orbit. The picture taking shape in the data was not what anyone had fully expected. Mercury's rotation, as measured from orbit with far greater precision than radar observations from Earth had allowed, turned out to be not perfectly smooth. It wobbles very slightly, very measurably. The technical term is physical libration, a tiny oscillation in the rotation rate superimposed on the average 2 spin-orbit resonance. The amplitude of this wobble depends on the interior structure of the planet. Specifically, it depends on whether the core is solid or liquid. If Mercury's entire interior were solid, frozen through, the whole planet would respond as a rigid body to the gravitational torques applied by the Sun. The libration amplitude for a fully solid Mercury can be calculated. If Mercury's core is at least partially liquid, however, the outer shell decouples from the interior. The mantle and crust rotate as a unit, while the liquid core does not fully follow. The libration amplitude for this configuration is different, larger, because a smaller effective mass is being torqued. Messenger measured Mercury's libration amplitude. The value was inconsistent with a fully solid interior. It matched the value expected for a planet with a liquid outer core, a shell of molten iron surrounding a solid inner core, similar in broad structure to Earth's interior, but with very different proportions. Mercury has a liquid outer core. This was the confirmation that the Mariner 10 magnetic field detection had implied but not proven. The field exists because the outer core is still liquid, still convecting, still generating the dynamo that produces the magnetic field. But the question of why Mercury still has a liquid core, why it has not frozen solid in the 4.5 billion years since its formation, is more complex. A planet of Mercury's size and composition should, by standard cooling models, have solidified long ago. The current best hypothesis involves sulfur. If Mercury's core contains a significant fraction of iron sulfide, a compound of iron and sulfur, the melting point of the core material is depressed substantially compared to pure iron. A lower melting point means the core stays liquid at lower temperatures, which means it stays liquid longer as the planet cools. Messenger's sulfur measurements at Mercury's surface, the gamma-ray spectrometer detected sulfur concentrations several times higher than expected, are consistent with a sulfur-rich interior. The sulfur concentration at the surface implies a sulfur-rich bulk composition, which implies a sulfur-bearing core, which helps explain why the core remains at least partially molten. One element, one compound, and it changes the entire thermal history of the planet. There is something else about Mercury's magnetic field that Messenger resolved with a level of detail the Mariner 10 flybys had been unable to provide. The field is not symmetric. On Earth, the magnetic field is approximately dipolar. It looks, in first approximation, like the field of a bar magnet sitting at Earth's center, aligned roughly with the rotation axis. Mercury's field is also dipolar, but the center of that dipole is not at Mercury's center. It is offset northward, displaced along the rotation axis toward the North Pole by approximately 480 kilometers. This means the magnetic field in Mercury's northern hemisphere is stronger than the field in the southern hemisphere. The difference is significant. At Mercury's northern surface, the magnetic field reaches approximately 400 nanoteslas. At the southern surface, closer to the equator of the displaced dipole, the field is weaker, providing less shielding from the solar wind. The solar wind, the constant outflow of charged particles from the sun, interacts with planetary magnetic fields at a boundary called the magnetopause. At Earth, the magnetopause sits at roughly 10 Earth radii on the sunward side, a substantial buffer zone between the solar wind and Earth's surface. Mercury's weaker and asymmetric magnetic field creates a much smaller magnetosphere. At Mercury, the magnetopause on the sunward side sits at only about 1.4 Mercury radii, a thin shell of magnetic protection pressed close against the planet. The southern hemisphere, with its weaker field, is even more exposed. The solar wind particles that penetrate the southern magnetosphere impact the southern surface with essentially no magnetic shield. The surface is being directly struck by the sun. The implications for Mercury's tenuous exosphere, its wisp of an atmosphere, flow directly from this geometry. Messenger's atmospheric instruments measured the composition of the exosphere with high precision. Mercury's exosphere is not an atmosphere in the conventional sense. It is too thin for that. The gas pressure at Mercury's surface is roughly 10 to the negative 14 bars, approximately 100 trillionth of Earth's sea level atmospheric pressure. The particles in this exosphere are so sparse that they almost never collide with each other. They behave more like independent ballistic projectiles than like a gas, each molecule or atom following its own arc from the surface into space and back again, or escaping the planet entirely. The dominant species detected by Messenger included sodium, oxygen, hydrogen, helium, calcium, and magnesium. Each element has a different source mechanism. Sodium and calcium are primarily produced by micrometeorite impacts, tiny particles striking the surface at high velocity, vaporizing on contact, and releasing surface material as a cloud of atoms that briefly becomes part of the exosphere. Hydrogen and helium are captured directly from the solar wind. Particles that strike Mercury's surface become neutralized and bounce back upward as neutral atoms. Magnesium and oxygen, along with sodium, are also contributed by a process called photon-stimulated desorption. UV photons from the sun striking the surface and loosening atoms from their mineral lattice bonds. And by sputtering, the impact of energetic ions from the solar wind directly ejecting surface atoms into the exosphere. The combination of these processes means Mercury's exosphere is dynamic and variable. It changes with Mercury's position in its orbit. Near perihelion, when the planet is closest to the sun and solar wind intensity and UV flux are highest, the exosphere is more active. At aphelion, the rate's slow. The tail of Mercury's exosphere, the stream of escaping atoms pushed anti-sunward by solar radiation pressure, extends for millions of kilometers behind the planet. This tail has been detected from Earth. Sodium atoms glowing with resonantly scattered sunlight, streaming away from Mercury in a comet-like tail, despite Mercury being a rocky planet with no volatile ice to drive a comet's activity. This tail is a slow erosion. Over billions of years, Mercury has been losing surface material to space. Atom by atom, the solar wind and UV radiation stripping the surface, the exosphere carrying the material away, the tail marking the direction of loss. How much Mercury has lost is difficult to calculate precisely, but the stripping has been ongoing since Mercury formed. And for those billions of years, alongside the erosion, something else has been happening at Mercury's poles. Something that requires one more piece of data, the radar observations from the 1990s that gave the first hint, and then the messenger neutron spectrometer data that made the case. Mercury has ice. Not everywhere, not exposed, but present. And its location and what it means for the history of this planet is the next piece of what Mercury has spent billions of years quietly keeping to itself. In 1991, astronomers pointed the Goldstone Solar System radar in California toward Mercury. The radar dish transmitted a beam of microwave energy at the planet and waited for the return signal. What came back was unexpected. Certain regions near Mercury's poles reflected the radar with an intensity and a polarization signature that matched almost exactly the radar return from water ice. Not rock, not metal, ice. The same radar signature seen from the polar ice caps of Mars, from the icy moons of the outer solar system, from comets. The researchers were careful. They considered alternatives. Could the signature come from some other material, a sulfur compound perhaps, or a silicate that happened to reflect microwaves in a similar way? The models were checked. The alternatives did not fit as well. The water ice interpretation was the most consistent with the data. But the data came from Earth-based radar, and radar has limited spatial resolution at planetary distances. The bright polar anomalies could be localized to specific features on Mercury's surface, but which features exactly required a spacecraft in orbit? Messenger carried a neutron spectrometer as part of its gamma-ray and neutron spectrometer instrument package. Neutron spectrometers detect the energy spectrum of neutrons produced when cosmic ray particles strike a planetary surface and cause nuclear reactions. Hydrogen is particularly effective at slowing neutrons. When a neutron spectrometer detects a region of unusually low-energy neutrons, thermal neutrons, it is detecting the presence of hydrogen-rich material. And the most common hydrogen-rich material in the solar system, besides gas giant atmospheres, is water. As Messenger's orbit carried it repeatedly over Mercury's north polar region, the neutron spectrometer recorded a clear signal. A depression in the flux of epithermal neutrons, neutrons in the energy range between thermal and fast, precisely correlated with the locations of the radar-bright anomalies seen from Earth. Hydrogen? Concentrated. Sitting in specific locations at Mercury's north pole. The Messenger laser altimeter data provided the critical context. The MLA had been building a topographic map of Mercury's northern hemisphere throughout the orbital mission. When that topographic map was overlaid with the radar-bright regions and the neutron spectrometer signal, the correlation was perfect. The radar-bright hydrogen-rich material was located inside craters. Specifically, inside craters whose geometry, their depth relative to their diameter, their wall height, their latitude, placed their floors in permanent shadow. Craters where the sun, even at Mercury's closest approach and most extreme seasonal geometry, never reaches the floor. The floors of these craters have not received direct sunlight in perhaps billions of years. And in that darkness, in that cold, the temperature on those crater floors has been measured by Messenger's thermal instruments at below -170 degrees Celsius. Some of the permanently shadowed craters near Mercury's pole maintain floor temperatures below -200 degrees Celsius. These are among the coldest naturally occurring surfaces measured anywhere in the inner solar system. In those conditions, water ice is stable. In those conditions, water ice delivered to the surface by cometary impacts, by asteroid impacts, by micrometeorite bombardment over billions of years, does not sublimate. It stays. On the planet closest to the sun, there is ancient ice that has never seen the light. The estimated volume of water ice in Mercury's permanently shadowed polar craters is substantial. Messenger data, combined with models of the ice deposit thickness, suggest a total ice volume on the order of 10 to the 14 kilograms, approximately 100 billion metric tons. This is comparable in volume to the ice deposits detected in permanently shadowed craters at Earth's moon, though Mercury's deposits appear, in some cases, to be thicker. Some of the ice deposits in Mercury's polar craters are covered by a thin layer of dark material, a surface coating that appears in the Messenger imagery as anomalously dark regions on otherwise bright ice. The composition of this dark material has been analyzed through Messenger spectral data. The leading interpretation is that it consists of organic compounds, carbon-rich molecules that were deposited along with water ice in cometary or asteroidal impacts and have been transformed by radiation processing over billions of years into a dark, refractory residue. Organic compounds. On Mercury, in the craters near its pole, the presence of organics on Mercury's surface is not evidence of biology. It is evidence of chemistry, the same chemistry that operates throughout the solar system, producing complex carbon-bearing molecules wherever the raw ingredients and energy sources are present. But it adds Mercury to the list of inner solar system bodies where the basic chemical building blocks associated with prebiotic chemistry have been detected. Mars, the Moon, asteroids, comets, and now Mercury. The ice and organics in Mercury's polar craters raise a question about delivery. How did this material get to Mercury? Mercury's orbit is not in a region of the solar system where comets and asteroids naturally linger. The intense solar radiation and gravitational focusing of the Sun make Mercury's neighborhood dynamically hostile to prolonged residence by volatile-rich small bodies. But impacts are not prolonged residence. Impacts are single events. Over 4.5 billion years of solar system history, the probability that comets and volatile-rich asteroids have struck Mercury is not zero. It is, in fact, quite high. The outer solar system contains vast reservoirs of water-rich material, the Kuiper Belt, the scattered disk, the Oort cloud, and objects from these reservoirs are continuously perturbed onto orbits that bring them into the inner solar system. Some strike Earth, some strike Mars, some strike Mercury. Each impact that delivers water to Mercury's surface releases water vapor into the tenuous exosphere. Most of that water is quickly destroyed, photodissociated by ultraviolet radiation, or swept away by the solar wind. But a fraction of the water molecules, before they can be destroyed, migrate across Mercury's surface in a random walk of thermal hops. Water molecules that arrive near the poles and find themselves above a permanently shadowed crater fall into that crater and freeze. They stay. They accumulate. Over billions of years, deposit by deposit, the ice builds up. The dark organic layer on top of some deposits suggests the ice has been there long enough for radiation processing to transform the surface material. Long enough for the carbon compounds to be cooked into something darker and more stable. This is not a recent phenomenon. This is a process that has been operating since Mercury's earliest history. The ice in those craters may be billions of years old. Outside the polar regions, Mercury's surface tells a different story. A story of heat, of stripping, of chemistry driven by proximity to the sun rather than preserved by distance from it. The hollows that Messenger discovered across Mercury's surface, those irregular, shallow, bright-floored depressions, unlike anything on the Moon or Mars, are now understood to represent the opposite extreme from the polar ice deposits. At the poles, volatile material accumulates in permanent shadow. Across the rest of Mercury's surface, volatile material is being removed. The hollows are where that removal is happening in real time, or what counts as real time on geological timescales. The current best model for hollow formation involves a class of minerals called sulfides, compounds of sulfur with metals such as calcium, magnesium, and iron, which have been detected in Mercury's surface material by Messenger spectrometers. These sulfide minerals are relatively stable at low temperatures, but when exposed to intense solar radiation, ultraviolet photons, solar wind ions, the energetic particle environment of Mercury's inner solar system location, they can decompose. The sulfur is released. The mineral lattice collapses. The surface material sublimates, vaporizes, or is sputtered away. What remains is a void, a shallow depression. The bright floors of the hollows are likely freshly exposed material, unweathered, not yet darkened by the space weathering that gradually darkens older surfaces exposed to the solar environment. The dark halos surrounding some hollows may represent the residue left behind as volatile material escaped, a concentration of the more resistant, less volatile components of the original mineral assemblage. Messenger images show hollows in various states of apparent development. Some are small and isolated. Some are large and coalescing, as adjacent hollows expand and merge into broader depressions. The observation that hollows appear to be actively forming, that they are not relics of ancient processes, but ongoing features, is significant. It means Mercury's surface is still changing. Slowly, incrementally, but changing. The solar environment is still stripping material from Mercury's surface, billions of years after the planet formed, and the evidence of that stripping is visible in the bright, irregular pits scattered across crater floors and peaks. Mercury is not a static, dead world. It is a world in slow, ongoing chemical interaction with the Sun. The exosphere directly reflects this. The sodium tail that streams away from Mercury, visible from Earth as a faint glow of resonantly scattered light, is fed partly by the same processes that create the hollows. Photon-stimulated desorption, sputtering, micrometeorite impact vaporization, all of these processes contribute atoms to the exosphere, and radiation pressure from the Sun pushes those atoms into the tail. Messenger measured the sodium exosphere in detail across multiple Mercury orbits and seasons. The sodium abundance varied with Mercury's position in its orbit, higher near perihelion when solar input was stronger, lower near aphelion. It varied with the local time of day on Mercury's surface, stronger on the day side where photon-stimulated desorption was active, weaker on the night side. It showed enhancements correlated with regions of active hollowing and with areas where the southern hemisphere's weaker magnetic field allowed more direct solar wind impact. The exosphere is not a fixed feature. It breathes with Mercury's orbit. It responds to every fluctuation in solar wind intensity, every burst of solar UV, every episodic enhancement of the solar energetic particle flux from solar flares and coronal mass ejections. Mercury sits so close to the Sun that it experiences the solar wind at full force, unmoderated by the distance that dilutes its intensity for outer planets. The solar wind at Mercury's orbit has a particle density and dynamic pressure roughly 5 to 10 times that at Earth's orbit. Mercury's thin magnetic field offset northward, doing its best. The interaction between the solar wind and Mercury's magnetosphere produces phenomena that Messenger documented in remarkable detail: magnetic reconnection events at the dayside magnetopause, where field lines from the solar wind and Mercury's field link and snap, releasing energy and driving plasma flows deep into the magnetosphere. These reconnection events are proportionally much more frequent and energetic at Mercury than at Earth. At Earth, Major magnetic reconnection events are associated with geomagnetic storms, disruptions to the magnetosphere lasting hours to days. At Mercury, the small magnetosphere cycles through equivalent configurations in minutes. The entire magnetosphere of Mercury can be reconfigured by the solar wind on timescales of a few minutes. On Earth, such changes take hours. Mercury's magnetic shield is thin, and the sun presses against it constantly. Through all of this, the stripping of the surface, the breathing exosphere, the dynamic magnetosphere being pushed and pulled by the solar wind, Mercury's interior has remained largely separate. The iron core deep beneath the crust and mantle generates its magnetic field and slowly cools. The lobate scarps at the surface record the contraction of the planet as that cooling proceeds. But the interior holds one more piece of the story. A piece that connects Mercury's present state to its origin, to the conditions of the early solar system that produced a planet with a core this large, a mantle this thin, and a history this complex. The question of how Mercury came to be this way is not settled. It has not been settled since Mariner 10 detected the anomalously large iron fraction. It has not been settled since Messenger confirmed the liquid outer core and measured the surface composition in detail. It remains, as of the most recent analysis of Messenger data, a question with competing hypotheses and insufficient data to choose definitively between them. And understanding that question requires going back, not to Messenger, not to Mariner 10, back to the beginning, to the first few million years of the solar system's existence, when the planets were not yet planets, and the material that would eventually become Mercury was still part of a vast, swirling, violent disk of gas and dust surrounding a newly ignited star. The disk that surrounded the early sun is called the protoplanetary disk, or the solar nebula. It formed approximately 4.568 billion years ago, when a cloud of interstellar gas and dust, likely disturbed by the shockwave from a nearby supernova, began to collapse under its own gravity. As the cloud collapsed, it spun faster, conserving angular momentum the way a figure skater spins faster when pulling in their arms. The central concentration of material ignited as the sun. The remaining material settled into a rotating disk extending outward for hundreds of millions of kilometers. In the inner regions of this disk, the region where Mercury now orbits, temperatures were high. Close to the newly forming sun, the temperature of the disk material was probably above 1,000 degrees Celsius in the very earliest phases, high enough that only the most refractory materials could exist in solid form. Refractory materials are those with the highest melting and condensation temperatures: iron, nickel, certain oxides of calcium, aluminum, and titanium. Volatile materials, water, carbon compounds, sulfur compounds, the building blocks of gas and ice, could not condense in the inner disk. They remained in the gas phase, distributed outward to the cooler regions of the disk. This temperature gradient is the fundamental reason the inner solar system planets are rocky, and the outer solar system planets are gas giants and ice giants. In the region where Mercury formed, the raw material was iron-rich, refractory, dense. The planetesimals, the kilometer-scale solid bodies that formed from the disk material and began colliding and accreting into larger objects, were composed primarily of iron and rock, with relatively low volatile content compared to the outer solar system. Mercury accreted from this material. It grew through collisions. Each collision added mass and released energy, heating the growing body. As Mercury's mass increased and its gravity strengthened, the rate of accretion accelerated. This is the standard picture of rocky planet formation, a picture that works reasonably well for Earth, Venus, and Mars. But for Mercury, the standard picture has a problem. Mercury is too small, or rather, its core is too large for its size. The proportion of iron in Mercury, the ratio of core mass to total mass, is far higher than expected for a body that formed through simple accretion of the material available in its region of the disk. Earth, Venus, and Mars all have iron cores that represent a smaller fraction of their total mass. Mercury's iron fraction is dramatically higher. Something happened to Mercury. Something that gave it an anomalously large iron core relative to its total size. Three main hypotheses have been proposed to explain this anomaly, and all three remain viable to varying degrees as of the most recent analysis of available data. The first hypothesis is the giant impact scenario. In this model, Mercury was originally a much larger planet, perhaps twice its current mass, with a more normal proportion of iron core to rocky mantle. Early in solar system history, when giant impacts between planetary embryos were common, Mercury was struck by a large impactor, perhaps a body 1/6 Mercury's mass, moving at high relative velocity. The impact stripped away a large fraction of Mercury's rocky mantle, the silicate material that makes up the bulk of Earth and the other terrestrial planets. The iron core, being denser and more centrally concentrated, was less efficiently stripped. What remained after the impact was a planet with a disproportionately large iron core and a thin, depleted mantle. This hypothesis is attractive because giant impacts are now known to have been common in the early solar system. The leading hypothesis for the formation of Earth's moon is a giant impact between the proto-Earth and a Mars-sized body. The formation of Uranus's extreme axial tilt is attributed to a giant impact. Giant impacts shaped the solar system. Mercury, having experienced one, is not inherently unlikely. The second hypothesis involves the early Sun. In its earliest phase, before it settled into the stable main sequence star it is today, the Sun was more luminous and produced stronger high-energy radiation. This intense early radiation may have been sufficient to vaporize and blow away the outer rocky mantle of the innermost planet. In this scenario, Mercury was reduced to its iron-rich remnant, not by a single catastrophic impact, but by a slow process of thermal stripping. The Sun gradually removing silicate material from Mercury's surface and upper layers over millions of years. This hypothesis has difficulty fully accounting for the degree of mantle depletion observed. The radiation levels required to remove as much mantle as Mercury appears to have lost are difficult to produce in standard solar evolution models. But the mechanism is real, and it may have contributed even if it was not the primary cause. The third hypothesis proposes that Mercury formed in a region of the solar nebula that was locally enriched in iron, that the raw material available in Mercury's formation zone happened to have a higher iron fraction than the material available in the zones where Venus and Earth formed. Variations in composition across the protoplanetary disk are expected. The disk was not perfectly mixed. Different regions experienced different temperatures, different levels of turbulent mixing, different exposure to the evaporation front, the boundary between the region where iron-bearing minerals could condense and the region where they remained as vapor. If Mercury formed in a locally iron-rich zone, no giant impact or atmospheric stripping is needed to explain its large core. The iron was always there. It was always in the proportion observed. Messenger's surface composition data has been used to evaluate these three hypotheses with mixed results. The giant impact hypothesis predicts that Mercury's mantle should be severely depleted in volatile elements. The stripping impact would have released enough heat to vaporize most of the easily vaporized material. But Messenger found high concentrations of sulfur and potassium at Mercury's surface. Both sulfur and potassium are volatile elements. Both should have been depleted if Mercury had experienced a high-energy giant impact that melted and partially vaporized the mantle. Their presence is difficult to reconcile with the simplest giant impact models. The planet does not fit the model built to explain it. Some researchers have proposed modified giant impact scenarios, lower velocity impacts that removed mantle material without generating enough heat to drive off volatiles, or impacts early enough in Mercury's history that subsequent volcanic activity could have redistributed volatile elements back toward the surface. Others have suggested that the iron-enriched disk hypothesis best accounts for the compositional data, and that Mercury's large core is simply a consequence of where in the disk it happened to form. The question remains open. BepiColombo, launched in October 2018 and currently in transit to Mercury, was designed in part to evaluate exactly these competing hypotheses, with instruments more precisely calibrated for surface composition than Messenger carried. The data BepiColombo will return from Mercury orbit may finally allow planetary scientists to choose between the giant impact, the thermal stripping, and the iron-enriched disk scenarios. Or it may reveal a fourth possibility no one has fully considered yet. Mercury has a way of surprising the people who study it. It surprised Leverrier. It surprised the team that believed it was tidally locked. It surprised the Mariner 10 scientists who did not expect a magnetic field. It surprised the Messenger team with its volatile-rich surface and its polar ice and its active hollows. The history of Mercury science is a history of confident expectations being quietly overturned by data. And so the question of how Mercury came to be this way remains suspended, held open by the weight of conflicting evidence, waiting for the next data set, the next measurement, the next spacecraft. Outside, on Mercury's surface, none of this uncertainty is apparent. The craters do not know they are evidence. The scarps do not know they are arguments. The ice in the polar shadows does not know it is a clue. Mercury exists in its orbit, 57.9 million kilometers from the Sun at its mean distance, completing one orbit every 87.97 days, rotating once every 58.65 days, its iron core turning slowly within its shell of silicate rock, its magnetic field pressing weakly against the solar wind, its exosphere breathing in and out with the rhythm of the sun. This is what Mercury does. It has been doing it since the solar system settled into its current configuration, and it will keep doing it for a very long time yet. The formation of a solar system begins with violence. Not a single violent event, but an extended period of chaos, collisions, gravitational instabilities, material moving at velocities that make the word impact inadequate. The early solar system was not the orderly arrangement of planets and moons that exists today. It was a crowded, dynamic, dangerous place. Hundreds of planetary embryos, bodies ranging from the size of the Moon to the size of Mars, moved through the inner solar system on crossing orbits, colliding, merging, or deflecting each other into new trajectories. The surviving planets are the winners of that competition. They are the bodies that accreted enough mass to grow large and gravitationally dominant, clearing their orbital neighborhoods of competitors. Mercury survived, but the scars of its survival are written into its very structure. Understanding how Mercury formed, what it was made of, where it formed, what it lost, requires stepping back even further than the planetary embryo stage. It requires looking at the raw material. The protoplanetary disk that surrounded the early sun had a chemical gradient. Temperature decreased with distance from the sun. Close to the sun, where temperatures were highest, only the most refractory materials could exist in solid form. Farther out, where temperatures dropped, progressively more volatile materials could condense. This gradient produced a systematic variation in the composition of planetesimals across the disk. The condensation sequence, the order in which different minerals solidified out of the cooling nebular gas as the disk evolved, determined what material was available to build planets at each distance from the sun. At Mercury's formation distance, somewhere between roughly 0.3 and 0.5 astronomical units, based on current orbital models, the available solid material was dominated by iron, nickel, and high-temperature silicates. Volatile elements were largely in the gas phase. They had not yet migrated far enough outward to condense, or had been driven outward by the thermal gradient before condensation could occur. This is the baseline expectation for Mercury's composition: an iron-rich, volatile, poor world. And Mercury is indeed iron-rich. The core, as Messenger confirmed, represents approximately 83 to 85% of Mercury's total mass. The mantle, the rocky silicate layer above the core, is thin, estimated at roughly 400 kilometers thick, compared to Earth's mantle, which is nearly 3,000 kilometers thick. But the volatile content is wrong. The sulfur concentration at Mercury's surface, measured by Messenger's gamma-ray spectrometer, is approximately 4% by weight in some surface regions. Earth's silicate portion contains sulfur at roughly 0.025% by weight. Mercury's surface sulfur concentration is more than 100 times Earth's. Potassium, another volatile tracer, is present at concentrations broadly similar to Earth's, higher than models of high-temperature formation environments predicted. Chlorine, sodium, other elements with relatively low condensation temperatures are present in Mercury's surface material at levels inconsistent with simple formation from pure high-temperature refractory material. These measurements do not prove Mercury formed far from the Sun. They do not definitively rule out the giant impact hypothesis or the thermal stripping hypothesis. but they complicate the simplest versions of both. A Mercury that experienced a high-energy giant impact, the kind needed to strip away half or more of its original silicate mantle, should have lost most of its volatile inventory in the process. A Mercury that was thermally stripped by the intense early solar radiation should show a similar volatile depletion. Instead, Mercury has kept its sulfur, kept its potassium, kept in the shadows at its poles, its water. The planet resists simple explanation. BepiColombo, launched in October 2018 on an Ariane 5 rocket from the Guiana Space Center in French Guiana, is on its way to provide the next chapter of data. The mission is a joint project between the European Space Agency and the Japan Aerospace Exploration Agency, the first time these two agencies have collaborated on a planetary science mission of this scale. BepiColombo actually consists of two separate orbiters: the Mercury Planetary Orbiter, built by ESA, which will study Mercury's surface, geology, composition, and interior, and the Mercury Magnetospheric Orbiter, built by JAXA and named MEO, which will study Mercury's magnetic field, magnetosphere, and the interaction between Mercury and the solar wind. The two orbiters are currently traveling together, stacked in a configuration called the Mercury Transfer Module, which uses a combination of solar electric propulsion, ion thrusters powered by large solar panels, and a series of planetary gravity assists to navigate the long spiral trajectory toward Mercury. The mission's trajectory requires gravity assists from Earth, Venus, and Mercury itself. 6 Mercury flybys in total before the spacecraft reaches its final orbital configuration in 2026. During those flybys, BepiColombo's instruments have already been collecting data, returning images and measurements that have begun supplementing the MESSENGER dataset. The science questions BepiColombo is designed to address are direct extensions of what MESSENGER began. The elemental and mineralogical composition of Mercury's surface at higher resolution and with better calibration than MESSENGER's instruments allowed. The internal structure of Mercury, the thickness of the crust, the detailed density profile of the mantle, the size and state of the inner solid core nested within the liquid outer core. The three-dimensional structure of Mercury's magnetic field, measured simultaneously by the two orbiters in different orbits, allowing a true spatial map of the field rather than the time-averaged single spacecraft measurements MESSENGER provided. The dynamics of Mercury's magnetosphere, how it responds to the solar wind on short timescales, how magnetic reconnection events propagate through the system, what particle populations exist within the magnetospheric boundary, the composition and variability of the exosphere, building on MESSENGER's measurements with instruments calibrated for different wavelength ranges and higher sensitivity, and ultimately the origin question. Where did Mercury form? What happened to its mantle? Why does its core contain so much iron? These are the questions the mission is carrying across 7 years of interplanetary travel. 7 years following a path designed by mathematicians who understand orbital mechanics well enough to use the gravity of planets as a fuel substitute. The same fundamental technique that Mariner 10 used in 1974. The same insight that Giovanni Colombo provided, that the solar system's own architecture can be used to reach places that direct propulsion alone cannot. While BepiColombo travels, Mercury continues its orbit. An orbit of 88 days. a dayside temperature of 430 degrees Celsius, a nightside temperature of negative 180. The great compressional thrust faults still standing across the cratered plains, running for hundreds of kilometers, the surface expression of a planet contracting around its cooling interior. The lobate scarps of Mercury, Discovery Rupes, Santa Maria Rupes, Adventure Rupes, Beagle Rupes, are among the largest tectonic features in the inner solar system. Discovery Rupes, one of the largest, extends for approximately 650 kilometers and reaches heights of up to 3 kilometers above the surrounding terrain. It cuts across older craters, displacing their floors and walls along the fault surface, recording in stone the moment when Mercury's contracting interior pushed the crust up and forward. The contraction is still ongoing. Not at the rate it once was. The cooling has slowed as Mercury's interior temperature has dropped over billions of years, but it has not stopped. The planet is still tightening. Recent analysis of high-resolution messenger images identified young scarps, fault structures with relatively sharp morphology, not yet softened by the slow erosion of micrometeorite bombardment that gradually smooths older features. The estimated age of these young scarps, based on the crispness of their topographic signature and the crater count on their surfaces, suggests they formed within the past several 100 million years. Geologically recent, not ancient. Mercury has been tectonically active in the specific sense of crust movement driven by interior cooling within an era that is recent by solar system standards. This is a planet still in motion, slowly, inexorably, contracting around its cooling iron heart. On the surface, the evidence of this contraction is quiet and still. The scarps do not move on human timescales. The craters do not change perceptibly over a human lifetime. Everything on Mercury appears frozen. But frozen is relative. On geological timescales, Mercury is active. On astronomical timescales, Mercury is also changing in a way that has nothing to do with its interior. Its orbit is changing, slowly, over very long timescales, and the trajectory of that orbital change leads somewhere unexpected. Computer simulations of the long-term gravitational dynamics of the solar system, simulations that run the equations of gravitational interaction forward for billions of years, have revealed a troubling instability in Mercury's orbital future. Mercury's orbit is sensitive to the gravitational perturbations of the other planets, particularly Jupiter. Jupiter, the most massive planet in the solar system, sits far from Mercury, but its gravitational influence is not zero at Mercury's distance. Over very long timescales, the accumulated gravitational nudges from Jupiter and the other planets cause Mercury's orbital eccentricity to drift. Normally, this drift is bounded. Mercury's eccentricity oscillates within a range, increasing and decreasing over millions of years, but staying within relatively safe limits. But simulations by researchers, including Jacques Lescar at the Paris Observatory, have shown that there is a small but non-zero probability, approximately 1%, based on the range of initial conditions considered, that Mercury's eccentricity could increase dramatically over the next 5 billion years. In the most extreme scenarios, Mercury's eccentricity could grow large enough that its orbit begins to cross the orbit of Venus. A Mercury with a Venus-crossing orbit would eventually have a close encounter with Venus. That encounter might result in Mercury being gravitationally scattered onto a new orbit. Or it might result in a collision. Mercury and Venus, two rocky planets, each billions of years old, meeting in a collision that would dwarf anything in the solar system's history since the late heavy bombardment. The probability is small, but it is not zero. In the most extreme version of this scenario, which Lascar simulations found to have a probability of roughly 1 in 2,000, the gravitational chain reaction triggered by Mercury's orbital instability could eventually destabilize the entire inner solar system, with Earth's orbit also being disrupted. These outcomes are rare. They are not predictions. They are the tale of the probability distribution, the unlikely outcomes that become relevant only when you ask what might happen over 5 billion years, not what will definitely happen. Most simulations show Mercury remaining in a stable orbit for the Sun's remaining main sequence lifetime. Most runs end with Mercury still orbiting, still processing through its 88-day year, still experiencing its 600-degree daily temperature swing. But the instability is real. The mathematics is sound. And it adds one more layer of strangeness to a planet that has spent its entire history defying expectation. For now, Mercury is where it has always been. Inner orbit, pressed close to the Sun, its surface baking and freezing in the rhythm of its slow solar day. Its core still molten enough to stir a magnetic field. Its poles harboring ice that has not seen sunlight in billions of years. Its exosphere breathing atoms in and out with the pulse of solar wind. And 2 spacecraft, one already gone, one still arriving, holding between them everything humanity has managed to learn about the innermost world. There is a particular quality to Mercury's surface silence that deserves its own attention. On Earth, silence is rare. There is almost always something, wind moving through leaves, the low-frequency rumble of distant machinery, the biological noise of insects and birds, and the shifting of soil. Even in the most remote places on Earth, the atmosphere carries sound. Mercury has no atmosphere in any meaningful sense. Its exosphere, the sparse scattering of sodium, oxygen, hydrogen, and helium, is too thin to conduct acoustic waves. Sound requires a medium. On Mercury, there is none. An impact could strike the surface 50 meters away, a small meteorite, perhaps half a kilogram, striking at 10 to 20 kilometers per second, and the event would produce no sound audible to anyone present. The ground would shudder. Seismic waves would propagate through the regolith and bedrock. A spray of ejecta would arc upward in perfect ballistic parabolas, following trajectories governed only by Mercury's 3.7 meters per second squared surface gravity and the geometry of the impact, with no air resistance to disturb them. And the whole event would happen in complete, unbroken silence. The silence of Mercury is not the silence of a quiet room or a remote valley. It is the silence of the absence of any medium through which vibration can become perception. Total, physical, absolute. The regolith on Mercury's surface, the layer of pulverized rock produced by billions of years of meteorite bombardment, has a texture that has been estimated from thermal emission measurements. It is fine-grained, loosely packed and excellent at trapping heat in its upper layers during the day, while also cooling rapidly when exposed to the night. A footstep on Mercury's regolith would produce no sound. The fine particles would compress slightly under the weight, releasing no vibration that could travel through air because there is no air. The footprint would remain in the regolith indefinitely. There is no wind to erode it, no rain to wash it away, no biological activity to disturb it. The only process that would eventually smooth that footprint is micrometeorite bombardment, the slow rain of tiny particles that constantly churns the uppermost layer of regolith on airless bodies. On the Moon, where the same process operates, surface features smaller than a meter or two are typically obliterated within tens of millions of years by this gardening process. On Mercury, the higher velocity of impactors due to Mercury's deeper position in the Sun's gravity well means micrometeorite bombardment may be somewhat more intense, but the process is slow by human standards. A footprint on Mercury would survive for a very long time. Looking up from Mercury's surface, the sky is black. Even in the middle of the day, with the sun blazing at an angular size 2 to 3 times larger than it appears from Earth, the sky surrounding it is black. Because there is no atmosphere to scatter sunlight sideways into a blue dome, the sky above Mercury's surface is the sky of space, the deep, constant black of the void, stars visible even during the day if the sun's direct light is blocked. The sun itself, seen from Mercury's surface near perihelion, spans an angular width of approximately 1.7 degrees. From Earth, the sun spans about 0.5 degrees. From Mercury at perihelion, the sun is more than 3 times larger in apparent diameter. Its surface detail would be visible to the naked eye in a way impossible from Earth: granulation, the texture of solar convection cells, sunspots if present, the magnetic loops of prominences arching above the limb. But observing the sun from Mercury's surface unprotected would be fatal almost instantly. The solar irradiance at Mercury's perihelion distance, the intensity of sunlight, reaches approximately 14,446 watts per square meter. Earth receives approximately 1,361 watts per square meter. Mercury at perihelion receives more than 10 times as much. Every square meter of Mercury's sunward surface absorbs an energy flux that would destroy most known materials if sustained for long enough. The surface reaches 430 degrees Celsius, not because of some exotic property of Mercury's geology, but simply because it is sitting in the full intensity of the sun's output from a distance of 46 million kilometers, with no atmosphere to distribute that energy and no water to absorb or moderate it. The rocks absorb. The rocks heat. The rocks radiate. And then the sun sets. On Mercury, sunset is not the gradual dimming of Earth's sunsets, softened by atmospheric scattering and refraction. On Mercury, the sun simply descends toward the horizon, which with no atmosphere is razor sharp, and disappears. The transition from day to night is not gradual. The temperature begins to fall immediately. Mercury's surface material, with no atmospheric blanket to slow the loss of heat by radiation, cools rapidly. The rate of cooling in the hours after sunset on Mercury is among the fastest measured for any solid surface in the solar system. Within the first hour after sunset, surface temperatures can drop by more than 100 degrees Celsius. Within a few hours, the temperature has fallen below zero. By local midnight, roughly 44 Earth days after sunset, at the equator, the surface has reached its minimum of approximately -180 degrees Celsius. Then the slow arc toward the next sunrise begins. 176 Earth days from one sunrise to the next. One Mercurian solar day. And in the permanently shadowed craters at the poles, none of this daily cycle is felt. The floors of those craters are locked in perpetual cold. The ice that accumulated there, deposited by cometary and asteroidal impacts over billions of years, sits undisturbed. The temperature remains constant, or nearly so, for geological eras. The difference between the pole and the equator on Mercury is not merely a matter of temperature. It is a matter of geological time. At the equator, the surface is reset thermally every 176 Earth days, heated to temperatures that chemically alter minerals and drive off volatiles, then cooled to temperatures where different reactions dominate. At the pole, inside those lightless crater floors, nothing has changed in a very long time. The ice has been sitting there since it was deposited, unchanged, patient, in the dark. Mercury is a world of extremes held very close together in space. A few kilometers from the equator toward the pole, the thermal environment changes dramatically. A few kilometers deeper into a shadowed crater, the temperature drops by 200 degrees. On one face of the planet, full intensity sunlight. On the other face, the cold of deep shadow. The iron core still partially molten, generating a magnetic field 1% the strength of Earth's, pressing weakly outward against a solar wind that presses inward constantly, the boundary between them never far above the surface. This is Mercury at this moment. This is Mercury as BepiColombo approaches. This is Mercury as it has been, with small variations, since the age of the solar system began. The smallest planet in the solar system. The one with the largest iron core relative to its size. The one whose surface theory predicted would be stripped of volatiles and yet retains sulfur, potassium, water. The one with a magnetic field no model fully predicted. The one whose orbital anomaly pointed the way to general relativity. The one that keeps surprising the people who study it. Mercury does not fit the models built to explain it, and it has never apologized for that. The data that MESSENGER collected over its 4 years in orbit, more than 270,000 images, 10 terabits of scientific data, measurements of gravity, magnetic field, surface composition, atmospheric composition, particle environment, has been the primary source of Mercury science since the mission ended in April 2015. Researchers around the world continue to work through that dataset, publishing new findings, refining models, testing hypotheses against the measurements. New papers on Mercury appear regularly, on the formation of hollows, on the magnetic field asymmetry, on the polar ice deposits, on the chronology of volcanic activity, on the structure of the core. The mission is over, but the science continues. Science from a single spacecraft that took us 7, 9 billion kilometer path through the inner solar system to reach a planet 77 million kilometers away. The ratio of those two numbers, 7.9 billion divided by 77 million, is approximately 100. The spacecraft traveled 100 times the straight-line distance to Mercury to reach it. 100 times farther because the straight line was not available. Because physics and orbital mechanics and the constraints of rocket propulsion required the long way. And the long way was worth it. Every measurement was worth it. Every image of those cratered plains, every reading of the magnetometer, every neutron count that pointed to hydrogen at the poles, all of it worth the 6 years and 7 months of interplanetary travel. Mercury had been waiting. Since Mariner 10 photographed 45% of it and left. Since Leverrier noticed the anomalous precession and had no explanation. Since the first Babylonian astronomers tracked a small, fast-moving point of light in the pre-dawn sky and wrote down what they saw. Mercury is still waiting, in a sense. Waiting for BepiColombo. Waiting for the next set of measurements that will move the origin question closer to resolution or reveal yet another layer of complexity that current models have not anticipated. The history of Mercury science does not give reason for confidence that the simple answer will be the correct one, but it gives every reason for confidence that the correct answer will be interesting. Whatever Mercury is, wherever it formed, whatever it lost, whatever keeps its core liquid and its magnetic field alive, the answer is not nothing. It is not a dead rock on a simple orbit. It is a planet that has been processing information about the inner solar system since the earliest epoch of planetary formation, encoding that information in its structure, its surface, its magnetic field, and its ice. BepiColombo is on its way to read more of that encoding. For now, Mercury turns in its orbit. 3 rotations completed for every 2 laps around the sun. The sun rises, moves backward, corrects itself, continues. The temperature climbs, falls. In the craters at the poles, nothing changes. The ice waits in the dark, patient, unchanged, holding its record of the ancient solar system in frozen silence. BepiColombo has been traveling for years. It is not a fast mission. It cannot be. The same orbital mechanics that made Messenger's journey so long apply to every spacecraft sent to Mercury. The laws of physics do not make exceptions for impatience. BepiColombo uses solar electric propulsion for much of its cruise phase, ion thrusters that expel xenon gas at very high velocity, producing a small but continuous thrust that gradually adjusts the spacecraft's trajectory over months and years. The specific impulse of an ion thruster, the measure of how efficiently it converts propellant mass into velocity change, is far higher than a chemical rocket. A chemical engine burns fuel in a brief, intense burst. An ion thruster pushes gently, continuously, for months at a time. The thrust from BepiColombo's ion thrusters is approximately 290 millinewtons at maximum, roughly the weight of a small orange, expressed as a force. Applied continuously for a year, that tiny force accumulates into a significant velocity change. Combined with the gravity assists from Earth, Venus, and Mercury during the cruise phase, This gentle, persistent push is sufficient to guide two scientific orbiters across the inner solar system and deliver them into Mercury orbit. The Mercury Transfer Module, the structure that holds the two orbiters together during the cruise, carries the ion thrusters and the solar panels that power them. At Mercury's orbital distance, those solar panels generate substantial power from the intense sunlight, but they must also survive it. The thermal challenge for BepiColombo is, if anything, more severe than it was for Messenger. The spacecraft's sunshields are designed to withstand continuous solar irradiance at Mercury's perihelion distance, up to 14,000 watts per square meter, for years at a time, while the scientific instruments behind those shields must be kept at temperatures compatible with electronic operation. The engineering margins are narrow. The qualification testing required to certify components for this environment was extensive. Several instrument components had to be redesigned or replaced during development when qualification testing revealed that the original designs could not survive Mercury's thermal environment over the planned mission lifetime. This is the physical reality of going to Mercury. Not just the orbital mechanics, not just the distance, but the heat. The constant, relentless, unmoderated heat of the inner solar system pressing against every surface of every structure that humanity dares to place there. When BepiColombo reaches Mercury and the two orbiters separate, they will enter different orbits optimized for their respective science objectives. The Mercury Planetary Orbiter, the ESA spacecraft, will enter a polar orbit with a periapsis of 480 kilometers and an apoapsis of 1,500 kilometers, giving it relatively low altitude coverage of the entire surface over the course of many orbits. The Mercury Magnetospheric Orbiter, JAXA's MEO spacecraft, will enter a higher orbit with a periapsis of 590 kilometers and an apoapsis of 11,640 kilometers, allowing it to sample the magnetosphere at a wide range of distances and altitudes. Having two orbiters simultaneously in different orbits is a significant scientific advantage. Messenger was a single spacecraft. When it measured Mercury's magnetic field, it measured it at one place at one time. To construct a picture of the three-dimensional magnetic field structure, it had to rely on measurements taken at different times in different orbital positions, and then combine them mathematically, a process that works well but introduces uncertainties related to the fact that the field may have changed between measurements. BepiColombo's two orbiters will measure the magnetic field at two different locations simultaneously. Simultaneous multi-point measurements allow direct separation of spatial variation from temporal variation, the ability to distinguish between a magnetic field that is structured differently at two locations versus a magnetic field that is changed between two measurements made at the same location at different times. This is a qualitative improvement in scientific capability. The magnetic field of Mercury, its asymmetry, its northward offset, its interaction with the solar wind, will be mapped with a completeness and three-dimensional resolution that Messenger's single spacecraft measurements could not achieve. The surface of Mercury will also be examined with new instruments. BepiColombo carries a higher resolution camera system than Messenger. The Mercury camera system on the MPO includes a high-resolution camera with a ground resolution of approximately 20 meters per pixel at periapsis, compared to Messenger's MDIS narrow-angle camera at approximately 18 meters per pixel, but with different coverage patterns. More importantly, BepiColombo carries spectrometers calibrated for different energy ranges and sensitivity thresholds than Messenger's instruments. The MIX instrument, the Mercury Imaging X-ray Spectrometer, is designed to map the elemental composition of Mercury's surface with higher spatial resolution than Messenger's XRS was capable of achieving. The Symbiosis instrument combines 3 imaging channels covering ultraviolet through near-infrared wavelengths, allowing mineralogical mapping of the surface material at a level of spectral detail that will distinguish between mineral groups and phases that Messenger's instruments could not separate. These improved compositional measurements bear directly on the formation question. The abundance and distribution of sulfur across Mercury's surface, measured at higher spatial resolution and with better sensitivity, will constrain the models of Mercury's interior sulfur content. The potassium to thorium ratio, which is used as a tracer of volatile versus refractory material in planetary surface compositions, will be mapped at resolution sufficient to identify regional variations. If Mercury's volatile content varies systematically across the surface, if ancient impact basins have different volatile signatures than highland terrain, or if volcanic plains differ from heavily cratered regions, that variation carries information about the geological history of the volatile elements, where the sulfur and potassium came from, how they were distributed, whether they were present in the original material that built Mercury or delivered later by volatile-rich impactors. The Messenger data already showed that Mercury's volatile content varies across the surface. BepiColombo will map that variation at a resolution where the geological context can be fully interpreted. The neutron and gamma ray spectrometer on the MPO MGNS will re-examine the polar hydrogen signal with improved sensitivity, potentially resolving individual deposits and constraining the depth of the ice at different locations. It may also detect variations in hydrogen content that correlate with specific crater ages or surface features, allowing the delivery history of water to Mercury's poles to be partially reconstructed. Water arriving at Mercury's poles. The history of that arrival, when it came, how much, from what source, is a chapter in the broader story of water in the inner solar system. Water is not as rare in the inner solar system as early planetary science assumed. The Moon has polar ice. Mars has water ice at its poles and possibly liquid water beneath the surface. Mercury has ice in its permanently shadowed craters. Even some near-Earth asteroids contain hydrated minerals, evidence that water was incorporated into their parent bodies during the early solar system. Water is carried throughout the solar system by comets and by the large fraction of asteroids that formed in the outer solar system and were subsequently scattered inward by gravitational interactions with the giant planets. Mercury, despite its position, has received its share. Not enough to form oceans, not enough to sustain liquid water on the surface under any conditions that have existed in Mercury's history, but enough to accumulate in the permanent shadows, enough to be measured, enough to be there. The same processes that delivered water to Mercury's poles may have contributed to the water inventory of the early Earth. The late accretion hypothesis, the idea that a significant fraction of Earth's water and volatile budget was delivered by cometary and asteroidal impacts during and after the late heavy bombardment, is supported by multiple lines of evidence. Mercury's polar ice deposits are a small, preserved example of the same delivery mechanism operating on the same body of objects. The comets and asteroids that built up Mercury's polar ice over billions of years are siblings of the objects that brought water to early Earth. Understanding Mercury's water history is, in this sense, understanding one small piece of Earth's water history. The solar system is not a collection of isolated worlds. It is a connected system, and Mercury's frozen poles are connected through the long reach of gravitational dynamics and impact history to the oceans of Earth. This perspective, the view from which Mercury is not a curiosity, but a data point in the history of the entire inner solar system, is part of what makes Mercury's science matter beyond the study of a single small planet. Mercury is the innermost. It has been exposed to the inner solar system environment longer and more intensely than any other planet. Its surface records processes that operated on all the rocky planets in the early solar system, but that have been partially erased on Earth by tectonics, erosion, and biological activity. Earth's oldest rocks are approximately 4 billion years old. Much of Earth's record of the first 500 million years of solar system history has been lost. Mercury's surface preserves terrain from that era. The ancient cratered highlands of Mercury are direct witnesses to the late heavy bombardment, to the conditions of the early inner solar system, to processes that shaped Earth before Earth had any record of being shaped. Reading Mercury's surface is, in a limited but real sense, reading a chapter of Earth's own history that Earth itself cannot provide. This is the scientific inheritance that Mariner 10 began collecting in 1974, that Messenger extended from 2011 to 2015, and that BepiColombo is traveling to continue. 50 years of looking at the planet nobody looked at. Each mission revealing more than the last. Each answer generating new questions. Each new question requiring a better instrument, a longer mission, a more precise measurement. And through all of it, Mercury has remained what it always was. Small, fast, extreme, close to the sun, full of iron, holding its water in the dark, defying every expectation that the people studying it brought with them. Tonight, above the permanently shadowed craters of Mercury's North Pole, BepiColombo's trajectory curves toward its destination. The spacecraft is still months away from orbital insertion. Its instruments are in cruise configuration, most of them powered down or in standby, conserving energy and surviving the thermal environment of the inner solar system. But the destination is there. Mercury is there, turning in its orbit. 3 axial rotations completed for every 2 complete orbits. The iron core slowly cooling. The magnetic field pressing outward. The solar wind pressing inward. The exosphere breathing. The ice waiting. The surface baking. The craters counting the years in their crater counts, one impact at a time, building the geological timescale that planetary scientists will use to interpret the next data set. Imagine a researcher, sometime in the late 2020s, sitting in front of a data terminal at a planetary science institute. The building is quiet. It is early in the morning, before the rest of the team has arrived. On the screen in front of her is a spectral map, a false color image of Mercury's surface derived from BepiColombo's symbiosis instrument, showing the distribution of mineral phases across a region of ancient cratered terrain in Mercury's southern hemisphere. She is looking at a pattern that does not match any of the models. A region of unexpectedly high magnesium abundance associated with a cluster of hollows in terrain that the crater counting chronology places at roughly 3.8 billion years old. The hollows are not supposed to be there. Hollows in the current models form in terrain that contains volatile-bearing minerals, sulfides, chlorides, compounds that sublimate under solar radiation. But this terrain is ancient. Ancient terrain on Mercury is supposed to be depleted of volatiles, stripped long ago by the intense solar environment. And yet the hollows are there. And they are fresh. Sharp edges, bright floors, not yet rounded by micrometeorite bombardment into the gradual softening that marks older surface features. She makes a note. She flags the coordinates. She adds this region to the priority list for follow-up observations in the next orbital pass. This is how planetary science advances. Not in dramatic revelations, but in the accumulation of anomalies, each one small, each one uncertain, each one requiring more data before it can be interpreted with confidence. The anomaly in front of her may turn out to be an artifact of calibration. It may be a real feature with an explanation that fits comfortably within existing models. Or it may be something that the existing models do not predict. Something that requires a new explanation. A new hypothesis. A new understanding of how Mercury's volatile inventory has been distributed and redistributed over 4.5 billion years of geological history. She does not know which of these possibilities is correct. That is the point. That is why the data matters. That is why BepiColombo traveled for years through the inner solar system to get here. Outside the Institute, the sky is beginning to lighten. Somewhere beyond that lightening sky, Mercury is completing another day. The sun is rising over its cratered plains. The temperature is climbing. The exosphere is brightening as sodium atoms scatter sunlight. The hollows on that ancient terrain are absorbing radiation, their volatile minerals slowly decomposing, the bright, shallow floors slowly widening. The BepiColombo orbiter is overhead, instruments running, recording. The data is being stored. In a few hours, it will be transmitted back to Earth, and someone will look at it. The planet is patient. It has been patient since the solar system formed. It will still be there when BepiColombo arrives. And it will still have questions that BepiColombo cannot fully answer. That is the nature of Mercury. That is the nature of science. Each generation of instruments is better than the last, and each generation of instruments finds the universe more complex than it appeared. The answers do not run out. They multiply. And somewhere in that multiplication, in the growing catalog of what is known and what remains unknown about the innermost planet, is a picture of the solar system's history that is still being assembled, one measurement at a time, across the silence of interplanetary space. There is a question that runs beneath all the specific science of Mercury, beneath the core size and the volatile inventory, and the magnetic field asymmetry, and the polar ice. It is a question about what it means to study a world, what it means to spend decades and billions of dollars and the professional careers of hundreds of scientists learning the detailed properties of a planet that no human will ever visit in their lifetime, and very possibly no human will ever visit at all. Mercury is not a candidate for human exploration in any current or near-term planning document. The thermal environment, the radiation environment, the lack of resources at the surface, the difficulty of the trajectory, all of these make Mercury an extraordinarily challenging destination for crewed missions. The robots go instead. Mariner Desi, Messenger, BepiColombo, these are the emissaries. They carry the instruments. They collect the data. They return it across the light minutes of separation between Mercury and Earth, compressed into radio signals at frequencies in the X-band or Ka band, transmitted at powers measured in tens of watts, received by dishes tens of meters across, built in the desert of California, or the plains of Spain, or the forests of Australia. The data arrives. It is processed. It is calibrated. It is distributed to researchers at universities and institutes around the world. And those researchers, working at desks and in seminar rooms and at computing clusters, reconstruct what the spacecraft saw and measured, turning the raw numbers into understanding. This is how humanity learns about Mercury. Through a chain of engineering and physics and mathematics and patient analysis that extends from the spacecraft in orbit to the scientist sitting with a dataset trying to understand what it means. The chain is long. The chain is slow. The chain works. Every fact known about Mercury came through this chain. The anomalous orbital precession that led to general relativity came from patient tracking of Mercury's position in the sky, night after night, year after year, by astronomers who did not know what they were building toward. The magnetic field came from a magnetometer on a spacecraft that almost did not survive its close approach to Mercury's thermal environment. The polar ice came from radar bounced off the planet from Earth, and then neutrons measured from orbit, and then images cross-referenced against topographic maps to find the permanent shadows. The volatile elements came from gamma rays and X-rays and neutrons detected by instruments calibrated against nuclear physics data acquired in laboratories on Earth. Every piece of this understanding has a history. Every measurement represents a choice to build this instrument rather than that one, to target this orbit rather than that one, to spend the money and the time and the intellectual effort on Mercury rather than on something else. Science is not an automatic process. It requires decisions. And the decisions made over 50 years of Mercury exploration have produced a picture of this planet that is genuinely strange. A planet smaller than 2 moons, closer to the sun than any other planet, covered in craters from a bombardment that ended 3.8 billion years ago, with scarps from compression that began at the same time and is still ongoing. A thin mantle atop an iron core of extraordinary size. A magnetic field that by all rights should not exist but does. A surface being slowly stripped by the solar wind and solar radiation, its volatile elements escaping atom by atom into an exosphere too thin to breathe, then swept away by solar radiation pressure into a comet-like tail. And at the poles, in craters that have been dark for billions of years, water, ice, and organic compounds. These are the facts of Mercury. They do not fit neatly together into a simple story. They require a planet with a complicated history, one that formed under specific conditions not yet fully understood, survived a bombardment that changed its surface permanently, possibly survived a giant impact or severe thermal stripping that removed most of its silicate mantle, cooled slowly enough to maintain a partially liquid core, and accumulated water in its polar shadows from the same comets and asteroids that delivered volatiles to the rest of the inner solar system. This is a history worth knowing, not because it has immediate practical consequences, not because Mercury offers resources or destinations that humanity will access soon, but because Mercury is part of the same solar system that produced Earth, and understanding Mercury's history is part of understanding how rocky planets form and evolve, knowledge that applies not only to Mercury, not only to this solar system, but to the thousands of planetary systems now known to orbit other stars. Exoplanet science has revealed that planets smaller than Earth, super-Earths, and sub-Neptunes are among the most common types of planet in the galaxy. Many of these planets orbit close to their stars. Many of them experience conditions that, in certain ways, may resemble what Mercury experiences: intense stellar radiation, strong tidal forces, potentially stripped or thin atmospheres. Mercury is the nearest laboratory for studying this class of environment. The physics of Mercury's core, the survival of its magnetic field, the fate of its volatiles, all of this has relevance beyond Mercury, applied to the interpretation of planets around other stars that will never be visited and may never be directly resolved in any telescope image. Understanding Mercury is understanding something general about how planets work. And so the work continues. BepiColombo approaches. The data from Messenger continues to be analyzed. Papers are written and reviewed and published. Models are tested and refined. Questions are replaced by better questions. And Mercury continues its orbit. An 88-day year cycling without interruption. The iron core maintaining its slow convection. The lobate scarps recording the planet's gradual contraction in stone. The Calories Basin, 1,550 kilometers across, holding the record of the most violent event in Mercury's geological history. The chaotic terrain at its antipode recording the shockwave that traveled through Mercury's body 4 billion years ago and arrived with enough energy to reshape the landscape. The hollows scattered across crater floors, bright and shallow, still forming, still growing, still marking the slow escape of volatiles from a surface that theory predicted would have none. The exosphere breathing, the magnetic field holding, the core turning, the ice waiting. Mercury is not sleeping. It is continuing. The same processes that shaped this planet from its earliest history are operating now. The solar wind is striking the surface. The atoms are escaping. The temperature is rising on the sunlit face and falling on the dark face. The craters are accumulating micrometeorite, impacts one at a time, their surfaces slowly gardened and mixed, their sharp edges slowly rounded by the patient rain of small particles. And in the permanent shadows at the poles, the ice sits exactly as it has for longer than any structure on Earth has existed. Patient, frozen, waiting for the light that will never come. This is what deep time looks like. This is what time looks like when nothing interrupts it. When no wind reshapes the surface. When no rain washes the craters clean. When no biology colonizes the regolith and changes its chemistry. Just the sun and the planet and the slow work of physics. The slow cooling of the interior. The slow stripping of the surface. The slow accumulation of ice in the dark. Mercury does not hurry. It never has. And it will not begin now. The days and nights cycle at their stately pace, each solar day 176 Earth days long, each sunrise preceded by the brief backward motion of the sun across the sky as Mercury reaches perihelion and its orbital velocity briefly exceeds its rotation rate. Every detail of that motion is calculable. Every position of Mercury at every moment in the future can be predicted with extraordinary precision using the equations of orbital mechanics and general relativity, the same general relativity that Mercury's anomalous precession helped confirm in 1915. Mercury helped prove the theory that predicts its own motion. It is this kind of entanglement between Mercury and the science done to understand it that makes studying the smallest planet feel, in the end, like something larger than the planet itself. Mercury is a world, but it is also a record of the early solar system preserved in stone and ice and iron, maintained in silence for billions of years, available to anyone with the instruments and the patience to read it. The instruments are getting better. The patience is being rewarded. The reading is ongoing. And what has been learned so far is enough to understand clearly that what remains to be learned is even more interesting. There is a moment in Mercury's year, if year can describe an 88-day orbit, when the planet reaches perihelion, its closest approach to the sun, 640 million kilometers. At that moment, Mercury is moving faster than at any other point in its orbit, nearly 59 kilometers per second, faster than any other planet moves at any point in its orbit. And from the surface, the sun appears at its largest, spanning nearly 2 degrees of arc, 3 times wider than it appears from Earth. The solar irradiance at perihelion is 14,446 watts per square meter. The surface temperature on the sun-facing hemisphere peaks at approximately 430 degrees Celsius. Lead melts at 327 degrees. Tin melts at 232 degrees. At Mercury's perihelion surface temperatures, both would be liquid. Zinc, with a melting point of 420 degrees, would be approaching its melting point. The rocks of Mercury's surface, silicates, metal sulfides, oxides, do not melt at these temperatures, but they are hot enough to glow dully in the infrared. Hot enough that the thermal emission from Mercury's dayside surface is detectable by telescopes on Earth and from orbit. Hot enough to destroy most electronic components without careful shielding. This is the environment that Messenger survived for 4 years. This is the environment that BepiColombo was designed to operate in indefinitely, or as indefinitely as mission funding and hardware lifetimes allow. The engineering required to place and operate a spacecraft in Mercury orbit is a direct confrontation with physics. The thermal engineers who designed the sunshields for these missions were not working with wide safety margins. They were working at the limits of what available materials could withstand. Ceramic cloth, polished metal surfaces, careful management of heat paths through the spacecraft structure, each element of the thermal design chosen because the alternative would fail. And yet the spacecraft worked. Messenger worked. BepiColombo is working. The hardware sitting in the inner solar system right now, surviving conditions that would destroy most machines, is a quiet demonstration of what careful engineering can achieve. There is something worth pausing on in that. Not for long, but for a moment. The fact that these spacecraft exist, that the knowledge of physics and materials science and orbital mechanics and electronics design accumulated over decades was sufficient to build machines that could survive Mercury's environment is not obvious. It required the accumulated work of thousands of people across generations, each generation building on what the previous generation learned. Mariner 10 taught messenger engineers what Mercury's thermal environment actually looked like, not just in theory but in practice. Messenger's performance in orbit refined the models that BepiColombo's designers used. BepiColombo's performance will inform whatever comes next. This is how the capacity to explore develops. Not in sudden leaps, but in gradual accumulation, each mission extending human reach a little further, refining human understanding a little more, enabling the next mission to go a little deeper. The night side of Mercury, while the day side bakes, is cooling. The cooling follows a curve determined by the thermal properties of the regolith, its specific heat capacity, its thermal conductivity, its emissivity. The regolith is not a uniform material. It is a complex mixture of pulverized rock, glassy spherules created by micrometeorite impacts, embedded metal grains from impactor material, and fine particles of varying composition. Its thermal behavior has been modeled extensively using data from Messenger's thermal instruments. The models predict and the measurements confirm that the temperature at a depth of a few centimeters below the surface does not experience the full daily swing felt at the surface. A few centimeters of regolith is enough to damp out most of the temperature variation. At a depth of approximately 10 centimeters, the temperature is nearly constant, close to the average between the day and night extremes, weighted by the length of time Mercury spends at each part of its orbit. This thermal stratification of the regolith means that the very uppermost surface layer, the part directly exposed to space, does the full thermal cycling. The layer below is buffered, and the rock below that is buffered further. The deep interior of Mercury, the mantle and core, is essentially decoupled from the surface temperature cycle. Its temperature is determined by internal heat generation and the slow process of cooling by conduction through the overlying material. This decoupling between surface and interior is fundamental. The surface of Mercury is one of the most thermally extreme environments in the solar system. The interior of Mercury is cooling slowly, on timescales of billions of years. Both are happening simultaneously in the same body, separated by a few hundred kilometers of silicate rock and tens of kilometers of crust. The slowness of the cooling matters. Every million years, the interior cools by some small amount. The core contracts slightly as it cools. The mantle adjusts. The crust, unable to contract uniformly, buckles and thrusts along the lobate scarps. The scarps grow imperceptibly. At a rate that Messenger could not measure directly, the timescales are too long, the motion too slow for even years of spacecraft observation to detect. But the cumulative effect of billions of years of this slow contraction is written clearly in the topography. The scarps are there. They are real. They are large, and they have been growing slowly for as long as Mercury has been cooling. Somewhere in Mercury's future, in the billions of years remaining before the Sun exhausts its hydrogen and begins its transformation into a red giant, the core will cool enough that the liquid outer core solidifies further. The dynamo will weaken. The magnetic field will diminish. At some point, the field will cease to be sustained by convection in the liquid iron. It will decay. Mercury will be left without a magnetic field, no shield, however thin, between its surface and the full force of the solar wind. The sputtering and photon-stimulated desorption that now supply the exosphere will intensify without magnetic deflection of solar wind ions. The rate of surface erosion will increase. The exosphere composition will shift. This is the future that awaits Mercury if the magnetic field dies before the Sun does. And the Sun will eventually do something far more dramatic than simply provide a stronger solar wind. In approximately 5 billion years, the Sun will exhaust the hydrogen in its core. The nuclear fusion that has powered the Sun for its entire main sequence life, the conversion of hydrogen to helium in the core, will cease in the core as the hydrogen runs out. The core will contract under gravity. The outer layers of the Sun will expand. The Sun will become a subgiant, then a red giant, swelling to a radius estimated at approximately 150 to 200 times its current radius. Mercury's current orbital distance from the Sun is 46 to 70 million kilometers. The Sun's red giant radius will be approximately 100 million kilometers. Mercury is inside that radius. As the Sun expands, Mercury will be engulfed. The planet will not survive the red giant phase. The thermal environment that Messenger and BepiColombo were engineered to endure, 14,000 watts per square meter at perihelion, will be replaced by the environment of being inside the outer atmosphere of a red giant star. Temperatures in the thousands of degrees, continuous intense radiation, direct contact with the stellar material. Mercury will be vaporized. Its silicate mantle, already thin, will evaporate. Its iron core, the iron heart that accounts for 85% of its mass, that has been cooling and generating a magnetic field since Mercury first formed, will eventually vaporize as well, its atoms dispersed into the stellar envelope of the dying Sun. Mercury will cease to exist as a distinct object. Its material will become part of the Sun, the same Sun that it has orbited for the entirety of its existence. The same Sun whose radiation has been stripping its surface, powering its exosphere, pressing against its magnetic field. In the end, Mercury goes back. But that end is 5 billion years away. And between now and then, there is time. There is a great deal of time. Mercury continues to orbit. The Caloris Basin, 1,550 kilometers across, holds the record of the most violent event in Mercury's geological history, its floor now a complex landscape of ridges and troughs, the chaotic terrain on the opposite side of the planet still standing as a monument to the energy that passed through the planet's body 4 billion years ago. The lightless polar craters hold their ice. They will hold it for a very long time. The ice will survive Mercury's orbital future, the possible eccentricity growth, the possible close encounter with Venus, because the ice is not affected by orbital changes. It is affected only by temperature, and the temperature in those craters is controlled by their geometry, not by their orbit. As long as the craters exist, as long as they are deep enough and located at high enough latitudes that the sun never reaches their floors, the ice will remain. The craters are old. They will not be erased quickly. The ice has time. BepiColombo is coming. When BepiColombo completes its long journey and the transfer module releases the 2 orbiters, each will fire its engine to enter its designated orbit. The instruments will be powered on, calibrated, checked, and the next chapter of Mercury data will begin. New images of the surface, new measurements of the composition, new maps of the magnetic field measured simultaneously from 2 different orbits for the first time, new neutron counts from the poles, new spectra of the exosphere, new gravity field measurements to refine the model of Mercury's interior. The data will take years to fully analyze. Papers will be written. Models will be updated. Some questions currently open will be closed. New questions currently not asked will open. And Mercury will continue. The planet that concealed the confirmation of general relativity in its orbital motion for 56 years. The planet whose core size broke every model built to explain it. The planet whose surface was predicted to be volatile-free and yet holds sulfur, potassium, organic compounds, and ice. The planet with a magnetic field that should have died billions of years ago. The planet whose polar craters contain water that has not seen sunlight since before complex life existed on Earth. Mercury, the planet that revealed to the Arecibo radar that it was not tidally locked as everyone had assumed, but locked in a more subtle and interesting resonance. The planet that surprised Mariner 10 with a magnetic field. That surprised messenger with ice and sulfur and organic compounds and actively forming hollows. Mercury is still surprising the people who study it. It will likely surprise BepiColombo. Not because Mercury is hiding anything deliberately, but because the universe is more complex than any single model, and Mercury sits in a region of that complexity that humans are only beginning to understand. The innermost planet, the one nobody looked at, still revealing itself, still turning, still waiting, out there right now in the full glare of the sun. There is a quality to Mercury's silence that is worth sitting with for a moment. Not the silence of an empty room. Not the silence of a forest at night, which is never truly silent, always full of the breathing of organisms, the movement of air through leaves, the distant evidence of biological life doing what biological life does. Mercury's silence is of a different kind entirely. It is the silence of a world where no medium exists to carry vibration, where the rocks absorb heat and release it, and the only sounds are seismic, the very occasional deep rumble of a micrometeorite impact propagating through bedrock, imperceptible on the surface because there is no air to carry it upward, no ears to receive it. Just the rock and the slow transmission of mechanical energy through stone. A geologist once described the airless surfaces of rocky bodies as the closest thing in the natural world to true mathematical abstractions, surfaces where the equations of orbital mechanics and thermodynamics operate without interference, without the complicating noise of weather or biology or geological activity. On Mercury's surface, the temperature at any given point can be calculated from first principles. Solar distance, albedo, thermal inertia, local time of day, latitude. Put these numbers into the equations and the answer comes out. Not approximately. With precision that Messenger's thermal measurements confirm to within the margins of instrument error. Mercury is a world where the physics is clean, where the equations work, where the universe behaves the way the equations say it should. And that cleanness, that transparency of mechanism is part of what makes Mercury a scientific treasure. Not just a curiosity, not just the smallest planet on an unusual orbit, but a laboratory. A place where the processes that govern all rocky planets operate without obstruction, legible in the data for anyone with instruments sensitive enough to read them. BepiColombo is reading them. The data is coming back. And the picture of Mercury, strange, small, extreme, full of iron and ice and impossibilities, is becoming clearer. One measurement at a time, one orbit at a time, one question answered and two more opened. This is what science looks like from the inside. This is what it has always looked like. If this story reached you tonight, if the science of this strange, small, extreme world found its way into your quiet, then you already know something that most people never think to ask. You know that the innermost planet holds water ice in craters no sunlight has ever touched. You know that the smallest planet has the largest iron heart. You know that a spacecraft spent 6 years on a 9 billion kilometer path to study a world 77 million kilometers away. You know that Mercury helped prove the theory that describes how gravity curves space. And you know that another spacecraft is on its way there right now. Still traveling, still closing the distance, carrying the next set of questions to a planet that has been accumulating the answers since the solar system was new. If this is your kind of story, a like and a subscription make a genuine difference to this channel. Every subscriber is someone who decided this kind of science was worth staying for. Thank you for being here tonight. Thank you for listening. Good night. Everything you heard tonight is real. Mercury is out there right now. The night side of Mercury is the quietest place in the inner solar system. Quieter than the surface of Mars, which has thin winds moving through its thin atmosphere. Quieter than the Moon, which at least has the faint seismic murmur of moonquakes. On Mercury's night side, with no atmosphere to conduct sound, no ongoing geological processes generating detectable seismic activity, no wind, no biological noise of any kind, the quiet is complete. The surface cools at its steady rate. The craters stand exactly as they stood. The regolith sits undisturbed except for the occasional micrometeorite, too small to be called an impact in any dramatic sense, striking the surface and disturbing a few grams of material in perfect silence. From above, the night side of Mercury presents no visible features. No city lights, obviously. No aurora because the magnetic field is too weak and the atmosphere too thin to produce the cascades of ionization that create auroras on Earth and Jupiter. But there are faint glows. Messenger detected a faint sodium glow at the poles, resonantly scattered sunlight from sodium atoms at the terminator and exosphere boundary, visible at ultraviolet wavelength. And there is the faint glow of the cosmic background, the omnipresent thermal radiation of the universe at 2.725 Kelvin, the afterglow of the Big Bang itself, present equally at Mercury and at Earth, and at the most distant reaches of the observable universe. Mercury is bathed in that ancient light, the same ancient light that surrounds every object in the universe. The same 13 8-billion-year-old photons that represent the universe's own memory of a time before stars or planets existed. These photons do not warm Mercury's surface. 2.725 Kelvin is far too cold to have any effect on a surface already at negative 180 degrees Celsius on the night side. But they are there. The cosmic microwave background is not a distant thing. It is everywhere. It was at Mercury when Mercury formed, and it will be there when Mercury is vaporized by the expanding sun, and it will be there long after, cooling slowly as the universe continues to expand until it reaches temperatures so close to absolute zero that no measurement we can currently imagine could distinguish it from nothing. Mercury exists in that light. It has always existed in that light. This is worth knowing, not for any practical reason, not for any immediate consequence, but because understanding where Mercury is, not just in the solar system, but in the universe, in the history of the universe, embedded in the relic radiation of the Big Bang, orbiting a middle-aged star in an ordinary galaxy, one of 4 rocky planets in a system that formed from the collapse of a molecular cloud fragment 4.568 billion years ago, is part of what it means to understand Mercury at all. Scale matters. The scale of Mercury's orbit, 57.9 million kilometers from the Sun, at mean distance, seems large until it is compared to the scale of the solar system. The scale of the solar system, extending to the outer edge of the Oort cloud at perhaps 100,000 astronomical units, seems vast until it is compared to the scale of interstellar space. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away, approximately 268,000 times the mean Earth-Sun distance. The solar system, including Mercury and its orbit, is a tiny structure in a galaxy of 200 to 400 billion stars. Mercury, at 4,879 kilometers in diameter, is smaller still. A point on a point on a point in the structure of the universe. And yet Mercury is known, measured, mapped, its iron core modeled, its magnetic field characterized, its polar ice quantified, its exosphere analyzed, its surface composition mapped at resolution sufficient to distinguish geological units and mineral phases. This small, extreme, complicated world has been understood to a degree that would have seemed impossible to the Babylonian astronomers who first tracked its motion across the pre-dawn sky. They could tell you where Mercury would be in the sky 6 months from now. We can tell you the sulfur concentration in its surface material. The distance between those two levels of understanding is the distance science has traveled in 4,000 years. It is not a small distance. Mercury is not sleeping, but the night side is still. The temperature is falling at the steady rate determined by the regolith's thermal properties. The craters that have held their shape for 3 and 4 billion years hold their shape still. In the polar craters sealed in perpetual shadow, the ice is exactly as it was. Nothing is changing on the timescale of a night. Nothing is changing on the timescale of a human lifetime. This is geological time. This is astronomical time. And in that time, the stillness is not emptiness. It is the stillness of processes so slow that they require billions of years to leave visible marks. The stillness of a cooling that has never stopped, not once, in all the time Mercury has existed. The stillness of an orbit so precisely governed by physics that every future position of the planet can be calculated centuries in advance. In that stillness, the science continues. In laboratories on Earth, the messenger data is still being analyzed. Models of Mercury's interior are still being refined. Thermal evolution codes are still being run, testing different assumptions about the sulfur content of the core, the initial temperature of the planet, the rate of heat production from radioactive elements in the mantle. Each run of the model is a test of whether the assumed conditions produce an interior that matches what the measurements show: a planet with a partially molten core, a magnetic field of measured strength and asymmetry, a crust of measured thickness and composition. The model that fits all of these constraints simultaneously is a model of Mercury's thermal history, a history of how this planet has changed over 4.5 billion years. Where it started, how it evolved, where it is going. The model is not yet fully constrained, but BepiColombo's data will help constrain it. And when BepiColombo's mission ends, when its fuel runs out, or its hardware fails, or its mission is declared complete, the data it has collected will continue to be analyzed for years afterward. The spacecraft dies. The data lives. This is true of Mariner 10, true of Messenger. It will be true of BepiColombo. The record accumulated by each mission becomes part of the permanent scientific heritage, available to any researcher, anywhere who wants to work on Mercury. And from that data, patiently, incrementally, the picture of Mercury grows clearer. The innermost, the most iron-rich, the most thermally extreme, the one whose orbital anomaly pointed the way to general relativity, the one that surprised every spacecraft sent to study it, the one with ice in its permanent shadows, and organic compounds in those shadows, and a magnetic field it should not have, and volatile elements it should not have kept. Mercury collects impossibilities, and it keeps them patiently in the cold and the heat and the silence of the inner solar system, waiting for the instruments that are good enough to read what they mean, waiting as it has always waited in the full glare of the sun, in, out, The orbit continues. The core cools. The ice holds. The science goes on. Good night. If you like this science story, please subscribe this channel, Quiet Science at Bedtime. Every new story is waiting now. Everything you heard tonight is real.